Awesome. Good morning, everyone. We're going to get started. We're going to go right on time. We have a lot of people here, and it's going to be a great morning. I really appreciate you giving about 3 hours for this course. We're going to go through a lot of great material. We're going to have some fun as well. 3 hours is a long time to kind of sit and kind of go through different things, but we're going to have a good time. We're going to take a couple breaks during the morning so we can kind of get some coffee. I need some coffee. You need some coffee. And what we'll do is when we're done, we're going to put together how to do an RT analysis in Whitson from beginning to end. And what I'm going to share with you this morning is the workflow that I use, and I have used over thousands of wells from around the world. And so what happens is when you have a set of steps, when you have a set instructions, what it allows you to do is approach data in a very systematic way. And this is helpful for a number of different reasons. One is, if you always approach it in a systematic way, whenever you share those results or show your analyses to anybody you work with, they'll be accustomed to the steps and kind of where there might be a deviation between the data of what we think is happening and what might actually be going on. So let me share my screen here. For those of you that I have not met yet, my name is James Ewert. I started with Fiquette a number of years ago, and after that, I went to Marathon Oil, and we were acquired by ConocoPhillips. And now I'm at Whitson, and it's a great pleasure to be here. And one of the things I'm very passionate about, I'm a hand talker, you're going to see this, is rate transient analysis. And so what I like to do is to work with people who have advanced skills in RTA, but also who are more introductory into it. And this course is more introductory, and it's going to kind of go through the software a little bit if you're new to the software and the environment, but also kind of how to systematically go through those steps. And so it's a great pleasure to have you with me this morning. One of the things I want to talk about before we jump into everything is you are at a training, which is fantastic. We have a lot of other training available. We have live webinars like what you're attending right now, but we also have webinars from the past that have been stored, and you can watch those videos. I believe this video will be able to be viewed in the future after it's done. So if you miss something, it's something you can catch up on a little bit later. But with Whitson, what we really care about is it's not just about a software package that you can use to analyze wells. We're really passionate about the community as a whole. And that means kind of the sharing of ideas. When someone figures out something that's really helping their analysis, having other people understand that and improve their analyses, it helps us as an industry as a whole. And so we're very passionate about that. For those of you new to Whitson, I want you to know that it's an all-in-one solution. We have RTA, PTA, nodal, decline, type well. We're always adding things. There's a lot of new features that we add, and we add them regularly. And so we're really proud of the product. It allows different team members from different disciplines, like production engineers and reservoir engineers and reserves folks, all to kind of communicate through the software using the same data. And it's a really powerful tool for that when working together as a team. Our support is absolutely fantastic. You can reach out to us at support@whitson.com. When we open the software, I'm going to show you where the button is where you can reach out to us, and we have a very quick response time, about a 2-minute response time. Now, during this morning, when we get into the software, if you have any issues whatsoever, you can put a message into the Teams chat. We have representatives from Whitson here to assist you. You can reach out to support directly. All of these things are here for you because we don't want not knowing where a button is to stop you from getting your work done. And so support is something, once again, we're also very passionate about. We have a fantastic team. Okay, so we're going to go through some slides before we actually jump into the material, but now would be a good time to make sure that your login is working. So what I would ask everybody to do is if you open up your web browser, I'm a Chrome guy. There might be some Edge folks, that's okay. But if you open up your web browsers, if you could go to courses.whitson.com. Now, all of you registered with an email. That's the email you want to use. And then the password is going to be RTA, all capital letters, course, all lowercase letters, 2026. And so as I kind of go through the slides, if you can log in, make sure it's working. If it's not, please drop a note in the Teams chat, and we'll get you sorted out. So I'm just going to take a moment now, let everybody load that up. We're not going to jump into the software just yet, but it's good that if you're logged in, because when we make that switch over, we want it to be as seamless as possible. Okay, so RTA, capital letters, course, smaller case letters, 2026. Excellent. Okay, so before we jump into the technical material, I wanted to share a story with you. It's a true story. And it was kind of my growth through the process of understanding RTA on one level, but then the business value on the other. And the business value side was the lesson. You just need, if you know me, you know I learned everything the hard way. And so this was something that happened, and I had to kind of go through this growth period. And I find that whenever we face a lot of challenges and you kind of get a little demotivated, that is an opportunity to raise the bar and grow. And it's really the choice, right? You either stay where you're at or you try to assess what's going wrong and try to be better than you were before. And so here's one of my stories. So when I worked at Phuket, it was fantastic. I would do RTA courses, kind of like this one, and I would analyze a lot of people's wells. And what I really valued was that I would bring value to the clients that we had. And so at that point, I was extremely confident in my RTA capabilities and what RTA could do for folks. But usually what would happen is people would send me their data and they would have a specific question. And I was very good at answering that specific question. And so I was very confident. You can see me sitting there with a smile and my coffee mug, very happy with myself, very pleased. Now, at some point, I decided I needed to leave the service side and go to an operator. I wanted to get in there and use the skills that I had to try to make money for a company. And Marathon Oil was kind enough to hire me, and there was a great group of people. I had great teammates. And so I went over there, and I thought I was going to go there, analyze the wells, find millions of dollars in value. Maybe I'd be CEO by the end of the year. You know, you never know. But I was really, really pumped, in fact, to go over there and really kind of show what I could do. And so you can see me smiling again. I'm very happy. I've got my books. I'm ready to go. And one of the first projects I was given was in Oklahoma. We were looking at a 3-mile well. It was kind of an outcrop well, okay? So we didn't have wells that had a similar geology or anything like that. So this was a great opportunity for RTA because if you can analyze wells in one area, you can then modify the parameters, those geological inputs, and generate a model-specific type curve or type well for that well. So I was really excited about it, and I worked really hard on it. It was probably 2 weeks, I think, Saturdays, Sundays, I really dug in. It felt like old school college days, right? Like I ordered pizza. I was going to impress everybody. And I think we've all had that moment, right? And maybe for some of the folks at the course today, where when you're new to a company, you really want them to know that they made the right decision hiring you. And so it's almost like you want to prove yourself. You want to be a valuable part of the team. And that's the pressure I was feeling at that time. And so this was my big opportunity. So I jumped in and I did a lot of work. And I think the work was really good. Okay. So at least I have that going for me. And so then came the time to present. And so I'm sitting there and I'm presenting my findings as to what I think this new well will do. I was very confident in my results. I had risked various things. And we had an engineer in the room. He's a very smart guy. I'm not going to use his name because I didn't ask for permission, but he's a great guy. And he was sitting there looking at all the work I had done. And he was just thinking to himself, this took all of this time to do. But I wonder what answer I would get if I just kind of did more of a statistical analysis, more of like a classic type well type analysis. And so when he approached me with that initially, I was thinking, well, it's going to be really different because, I've done, all this work and all this modeling and all this other stuff. And so he went back to his desk, and I put 20 minutes here, but it was probably 10. He came back to me and he said that his type curve for the proposed well was within 5 to 10% of my results. Now you can see my face here, okay? I'm a little disappointed because what took me 2 weeks to do at this deep level, applying everything that I had learned over the years, from a business perspective of whether we should move forward or not, he was able to figure that out in a sub-fraction amount of time. And so that kind of hit me like a bus. And so I kind of went through this thinking of like, what value do I actually bring to the team? How does RTA fit in to the business side? Because the business side just wants to know whether we should move ahead or not. I'm not going to say it's black and white, but it's more black and white than RTA, which adds a lot of gray to it. And so I went into Marathon. I was thinking that I was going to be Socrates, right? Like I had all this knowledge. I was going to be able to do all of these things. But after this happened, I felt like my name should be Mediocrities. And so I felt really kind of out of place, I think is the best way to say it. But I learned a very valuable lesson. And what I learned was that while my skills in RTA were there, I was misapplying them for what the business needed. Okay, so I was on the left-hand side. I was laser focused to try to get as good an answer as I could possibly get. When from the business perspective, that's not always required. Okay, so what I'm saying to you is RTA is a fantastic tool, but we want to know why we're doing it, which I mean, that makes sense when I say it. I feel like an idiot just saying that because I didn't know that. I just enjoyed the analysis. I enjoyed the science of it, but I would lose my goal. And from the business perspective at an operator, we need to know kind of what level of answer do we require? Do we need to do a deep dive? Sometimes you do, but not every single time. And so I learned a lot from that. And my takeaways really were after the years that I was there and then at Conoco afterwards, was RTA was extremely helpful when there's a specific question to answer. And let me give you some examples. RTA is absolutely fantastic in helping identify whether our decline curves are too optimistic. And the reason it's good for that is RTA will give you a sense of a contacted volume. A contacted volume is what it is, right? And so if the decline curve is saying we're going to get all of this volume out of this reservoir and the contacted volume and the fluid properties don't support that, then chances are you're not going to get that. So RTA is a great way to get another sense of whether our declines are in line or not. We used RTA to model Ewert degradation between high and low drawdown wells. And that's the thing is if you are drawing two wells down, if they're similar, if they're in the same type curve area and they've been drawn down differently, you can't really use a cum versus time plot to see which is the better well because they're going to have different curves based on how much they were ripped down. Now, RTA can use the pressures and the rates and compare those two with a value we call LFP, or the linear flow parameter. And really, that's the productivity of the well. We also used RTA to better understand the refracts we were doing. And so by using those geological parameters, we were able to identify that our refracts were creating a lot more height than fracture half length. And so RTA was extremely successful as a tool. And for me as a reservoir engineer, as a part of an asset team, when I had a specific question or specific goal that I was working towards, okay? Now, I'd like to analyze every well, and I analyze many of them. One of the takeaways, and it's kind of secondary to RTA, but it's still very helpful, was we analyzed all the flowback data for all of the wells we had, and it allowed us to see when you had parent wells and child wells, what the depletion was. And we were able to come up with a decay curve, which showed that if there was the distance and the cumulative volume produced before a new well came online, we could infer what the depletion would be for future infill and child wells. And that was also a fantastic use of RTA as well. So the skills we're going to go through today, the workflow that I'm going to teach you is one that has treated me extremely well over the years. But I would say to you that if you have a pad of wells and they have the same drawdown profile, cum versus time is a great way to get a sense of which wells are better, which ones are worse. And so when we use RTA, we want to make sure we have a goal, we have a focus, because it's easy to get lost in the analysis. And I say that as someone who's guilty of that, right? Because I just enjoy the process. But you know, at an operator, you have to have a deliverable. You have to have. I mean, it all comes down is what I'm advocating. Now, I've learned all those lessons, right? I'm a better engineer for it. A lot of the lessons, you know, you don't like them at first, but then you learn from them. And so have I peaked? Have I learned everything I need to know? I don't think so. I'm pretty sure there's more things that I'm going to learn along the way. But that's what makes the industry so compelling and so interesting is there is always more to learn. Now, I do hope that I passed the stupidest thing I've ever done, but you never know, right? You know, it's still, I'm young enough that maybe there's some runway there. But if you're going through that at a new company, we've all been through it. And I just hope the skills that we go through today are going to help you be successful. Now, before we jump into the software, we're going to go through some basics of RTA, but there's three things I really want you to know about the software. Now, it goes through a web browser. We recommend zooming at about 70 to 80%. Sometimes like 67% is what Chrome does. If you find when we're in the software that you don't see everything on the screen that you see on my screen, what that usually means is that you're zoomed in a little bit too much, right? So it's not difficult. You change the zoom and you'll be able to see all of the features we have in the software. The second one, some people do it. It's not my jam, but you can press F11 and you can go full screen, okay? So some people like to have that full real estate of their screen. I kind of just leave it the way it is. But the last one's really important. With web-based software, what we find is if there's any kind of wrinkles or anything in the internet connection or anything like that, if the software is not working exactly the way you think it should, all you have to do is do a refresh. Okay. Now, there's different ways you can do it with different browsers. For me, it's Control R. For other folks, it's, I believe, Control Shift R. But we also have a button in the software that I'll show you. You just click hard refresh, and everything just refreshes itself and will work as intended. So that last one's really important to keep in mind as we work through the software. Okay. So before we go through the workflow, before we analyze a well, let's go through some of the fundamentals. And the thing with RTA is that people can make it extremely complex very easily. But what we don't want to do is lose sight of the basics. And the basics are super important. And I find that when I see papers presented or anything like that, the basics tend to get muddled because of the complexities of the data that's being analyzed. And so what I want to tell you is that while RTA can be difficult with a specific data set, we need to respect those fundamentals. Those fundamentals is how we're going to get through it to a meaningful conclusion. Okay, and so that's what we're going to go through in the course this morning. Now, RTA kind of it's above kind of decline methods and rate time methods. We use pressure, so that's a big difference between decline and type wells, is RTA really needs those pressures to give context for those rates, right? Now, it's not a full hardcore reservoir simulation. There's reservoir simulators that are super huge. They can do mega things. They take a long time to run. They require a lot of data to input. RTA is using just the rate and pressure data from individual wells to get insights in there, right? So it's not meant to be a full field simulator, but you can get a lot of the information or results that you need from RTA from data that you already have stored in your database. So it's a fantastic tool. Now, RTA became really popular or increasingly popular as we move from a conventional world into an unconventional world. And this is all relating to something we would call material balance. In the conventional world, in order to understand how much was left in a vertical well, what you would do is you would shut in the well and you would get your average reservoir pressure and you could plot it and kind of get a sense of what your contacted volume was. And this worked great for millidarcy well, maybe even high microdarcy wells. But as the permeability came down with the targets that we were trying to achieve, when we got down to nanodarcy, if you shut in a well with nanodarcy perm, you were going to be there a while. And so having a manager shutting in a well for an extended period of time to understand how much was left in that tank, it was always a really hard sell. And so what we found was that with rate transient analysis, we could get a sense of the material balance. We call it a flowing material balance because it's using the flowing pressures and the flowing rates. And so we could use data we already had to calculate what the in-place volumes were. And that's why RTA really took off a number of years ago. And so it's really been a major component in unconventional wells. Now, one thing I would just say this to you, just so in case you wanted to know more about it from various sources or help file included. It's just a kind of a point in fact that I want you to know is that equations for RTA were developed for constant rate solutions, right? Does that change how you're going to analyze your well? No, but it's something that I just kind of want you to know. And the reason for that is if you look at the constant pressure one, the pressure kind of folds out almost like a wave or like a flower, okay? But constant rate does something really interesting. And what happens is if you have a constant rate solution, an idealized solution, when you hit bounded flow, the change in pressure at the reservoir extent is going to be the same at the change in pressure at the wellbore. And that observation, that knowledge allows the equations for RTA to work. So just as a point in fact, RTA was developed around a constant rate solution. And what you're going to see later on is we use something called material balance time. And material balance time is superposition for boundary dominated flow. And what that does is it takes variable rate data and makes it an equivalent constant rate solution. And so we can take variable rate data and fit it into those RTA equations. So that's just a little bit of background for you. Now, here's the only big equation I think I'm going to show this morning. It's just something to be aware of. Once again, a point of reference if you want to read more about it in the future. The RTA equation is actually called the pseudo-steady state equation. And so really what it comes from is Darcy's law gives us something called steady state flow. And so what Darcy's law is doing is it's describing the shape of this curve. Okay, now I want to draw your attention here. When we rearrange Darcy's law, it gives us the pressure within the context of average reservoir pressure versus wellbore flowing pressure. But remember, we're in a nano-Darcy rock. For us to get average reservoir pressure, we're going to have to shut in the well and wait a really long time. So we're not really interested in that. But when we think in terms of the compressibility and how that tank empties, compressibility gives us an equation for depletion. And so what turns the steady state into pseudo-steady state is that it's steady state, but it's depleting down through time. And we know that the delta P here is going to be the same as the delta P here because of what we observe from constant rate production. Now, here's the thing with depletion or compressibility, is it gives us another equation. But this equation sets pressure in terms of initial pressure and average reservoir pressure. And so what we can do is we can take those two equations and bring them together. And this does two things. One, it gets rid of average reservoir pressure. We don't have to shut in the well anymore. But what it also does is it sets our pressure relationship in terms of initial pressure and wellbore flowing pressure. The takeaway here is that the equations for RTA are constantly pointing back to your initial pressure of your reservoir. And so what I'm suggesting to you is that is an extremely important parameter to have and to have nailed down because it sets the context for the entire analysis that you'll do. So initial pressure, super important to have in the software. There's different ways to get it, and we can talk about that a little bit later. Here's the overall workflow. This is what we're going to walk through. Every step that we do in the software, I will relate it back to one of these four buckets. The first thing we care about is data diagnostics. We want to make sure that we're leveraging the data that we trust the most. In a lot of well histories, there's going to be data that's good and there's going to be data that's bad. Sometimes it's intermixed. We want to lean into that data that we think is giving us that reservoir signal that we want to capture. And so we want to filter out data points that we don't trust. We want to lean into that data that we think has the message that we want to receive. Now, how do we receive that message? That's interpretation. And interpretation is really the challenging part of RTA. Modeling's more fun. I'll get there in a second. But interpretation is where we're trying to listen to what the data is trying to tell us. And we do that with different tools. We use flowing material balance to get contacted volume. We can use a type curve to get a general sense of data quality. We can use numerical RTA to get our productivity or LFP. And so we're going to use all of these tools and we're going to try to listen to what the data is trying to tell us. Once we've done that, once we've described that reservoir signal in terms of parameters, that's when we go to a model. The primary purpose for a numerical model is to validate your interpretation. The model doesn't know what the answer is, but the model knows the rules of the game. It knows the physics and the rules of physics around a reservoir. So when we go to the model with our parameters and our production and pressure data, what we hope it will do is agree with us and give us a history match. And so the model should go through the history of the rates and the pressures that we have. And if we can do that, then we feel we can forecast it into the future with a higher degree of certainty than we would have with a normal ARPS decline, okay? Now, once we have a model that we're pleased with, we can then do forecasting, but it's more than forecasting. You can forecast it in EUR, but we can also do something called probabilistics. Typically, when we get geological parameters from our geologist friends, they'll give us a height, but it's usually a range, right? Or a porosity, it might be a range as well. Now, the height change can change what your fracture half lengths are going to be. And so we can run a probabilistic model with different heights, and it will calculate for us the range of fracture half lengths based on the uncertainty of the parameters that we've been given. And so that's another great part. So it's part of forecasting, but it kind of kicks it even further into its usability. So this is the workflow. I'm going to call back to it for the rest of this morning. Okay, now I talked about reservoir signal just a moment ago. I'm going to be very clear as to what I'm talking about. There's two idealized cases for reservoir signal. There's the constant pressure case, which I have on the left-hand side, and constant rate. What I'm saying to you is that if you take the pressure at the bottom of the well and you held it constant, so PWF is wellbore flowing pressure, right? The pressure at the bottom of the well, you hold that constant for a short amount of time. What's going to happen to your rate is you're going to have a Q1 up here, a Q2, and the shape of that curve. What I'm saying to you is that that curvature, the Q1, Q2, and the curvature has all the information the reservoir can give us. It can give us indications of its productivity and its volume. And from that, we can infer a fracture half-length minimum or permeability. Everything we want to hear from the reservoir is in there. Now, conversely, I take my rate, I hold it constant for a short amount of time. My pressure is going to act similarly. I'm going to have a P1, a P2, and a slope of this curve. And once again, that has the information that I care very much about in order to understand the well system that I'm looking at. Now let's look at this a slightly different way. On the right-hand side, I have raw data. Okay, now raw data can be messy. Typically it bounces up and down quite a bit. What I'm saying to you is that that second bucket, interpretation, what we're doing is we're taking this raw data and we're trying to extract out that reservoir signal. That's the point. And we're going to describe that reservoir signal with the different parameters that we have, like XF, K, FCD, etc. Now, once we think we've extracted that reservoir signal, when we go to the model, what we're telling the model is that if it's given this pressure, it should calculate this rate. Or if you get this pressure, it should calculate that rate because of this relationship we have between pressure and rate from the reservoir signal itself. And so interpretation is going from the raw data to reservoir signal, and the model, we're trying to build that reservoir signal back into the history to see if it's consistent or not. Now, there's a lot of different tools that we have to look at data. This is Louis Matar at the bottom left. He's a great man. He was one of my mentors at Phuket a number of years ago. And he was a huge advocate for looking at data in different ways, because different plots and different methods will stretch it in different ways, and it will make different things appear to us. And so what you'll see is we're going to use different methods to look at the data. And sometimes we're trying to answer the same question with different methods. But the reason we're doing that is because different things can poke their heads out, which might be of interest to us while we do that. And so I really advocate for the full workflow we're going to go through this morning. Some people try to do a quick method, which might work sometimes, but if it doesn't work or you're missing something, you would never know. So I always do the full workflow that we'll go through this morning. Now, flow regimes is an important component. We'll be talking about this when we get to flowing material balance. What I want you to know is there's three flow regimes that we really care about in unconventional wells. The first one is infinite acting flow. We call this linear flow. And this is when a well is its happiest, right? Because it's unbounded, it's wild and crazy, it's exploring that reservoir. And that's where we get a sense of what the productivity of the well is. Now, sometimes, not every time, but sometimes we're going to reach transitional flow. And what transitional flow means is that you're semi-bounded, right? The well has seen some boundaries, but we haven't seen some others, so there's still room for volume growth. Now, finally, we'll eventually hit something we call boundary-dominated flow. And what that means is we are totally bounded. Whatever volume we've heard from the data, that's all this well is going to see. And so we really want to know when we're trying to get a sense of the volume are we in linear flow? Like, is this a conservative volume? Are we going to see more? Or are we in boundary-dominated flow? And this volume that we have for this well, like that's all it's going to see. And so the EUR we get from the model is probably pretty close to the best that this well can do. Okay, so those are the three flow regimes, and we'll touch on those as we go through. I added this slide in here. I always think it's a little bit interesting. It doesn't really relate to the workflow necessarily, but it was something that blew my mind a number of years ago. If we had two wells and they were exactly the same, and we were producing them the exact same way, but at two different rates, the question is which well would see further into the reservoir than the other one, right? So I used gas units here, but if I had one at 0.01 million and then 10 million, but the wells were exactly the same, what can I expect my boundaries to be or my contacted volume to be? And it kind of blows my mind, but the truth is it should be the same, right? And so what I'm trying to say to you is that rate does not dictate how far that pressure pulse has gone into the reservoir. And this confused me for a very, very long time. And Louis Matar, who we spoke about a moment ago, gave me a great example of describing this. And so I want to share that with you. If you and I went to a pond and it was just nice, it was just glass, right? There's no wind or anything. And I took a small pebble and I threw it into the water. What we would find is that the ripples on the water wouldn't be very big, but the concentric circles would move through the water at a specific speed. And so then if you grabbed a bigger rock, because you're trying to one-up me, and I'm okay with that, I respect that. You take a bigger rock and you throw it into the water, what's going to happen? Well, the amplitude of the waves that you create are going to be bigger, but the pressure pulse itself is going to move at the same speed out from the point of impact. And that's because of hydraulic diffusivity. And hydraulic diffusivity doesn't have rate as a part of it. And so it's just something that I always thought was really interesting when thinking about how a reservoir works and what changes what we're viewing. Now, what I will tell you is that if you have a well with a higher rate, that if you think of the amplitude that we just talked about in terms of the waves that we created, that means that signal is easier to sense, okay? So while the pressure's moving out at the same speed, the more rate that we have, usually that response that we can sense is easier to see. And so that's something to keep in mind when we have low drawdown wells versus high drawdown wells. Now, some nomenclature we should go through here. Really, the top one is going to be the main one that we should focus on. Productivity of a well can be, there's different terms for it, and the terms have changed through time. Right now, the term that people tend to use is LFP, and that stands for linear flow parameter. I typically call it A root K or XF root K. And what it is that's how we get a sense of how productive this well can be. Now, the equation for this is 4 times XF, XF is our fracture half length, times NF, that's our number of fractures, times height, times the square root of permeability. Okay, and so that's kind of what dictates the productivity of our well. Now, when we think in terms of drainage geometry, for that, it'd be 2 times XF times LE or LW, and that's just the lateral length of our well. And for that, we're just kind of making the rectangle, the bounded system that we're looking at. Now, we know it's not two-dimensional. So we always add height. We have height in the software, of course. And so when we think of the total storage volume, that's when we're starting to think in 3 dimensions. But when we view these systems in the software, we're always looking at that plan view, that top-down view. So LFP, we're going to talk a lot about that coming up. It's really important for us to understand what RTA does and then what we do to try to be clever with what it does. Okay, let me explain what I mean. There are only 2 things you can sense from a well: productivity and volume. Okay, so those are the 2 components that we care about when we're trying to understand what a well is capable of or whether it's producing as well as it could be. Now, once we have that productivity, that LFP, that A root K, we have clever methods to deduce kind of what the permeability is and the fracture half length is, things of that nature. Same with contacted volume. But we need to understand that those are the 2 main things that we get from the data, and then everything from that is either derivative or drawn from that. But those are the 2 main pure things that we can get from a well, is LFP, productivity, and volume. Now, when we have a productivity and volume, usually if you have a type curve area that you've been given, or type curve areas that you've been given, you can really slot your wells into one of the 4 quadrants here. The first is tier 1, and this is great. Everybody loves the person who has tier 1 acreage. You're very popular. I'm very happy for you if you have some tier 1 acreage. And tier 1 means you've got high productivity and you have high contacted volume, right? So your wells are going to produce really well in the short term, and you have a long runway. You have a great EUR. Maybe you're exceeding what your type well was. You're having a great time in this type curve area. So those wells, they're perfect. Just leave them alone. They should be just fine. Now, there's other wells. We call these tier 2 wells, where you have a high productivity, which is awesome, right? But the contacted volume is lower. And that could be something we can learn from, because really what we would lean into is that the well spacing was too tight. We put too many wells per section into the section, and so they're too close together. And so this isn't something we can necessarily fix after it's been done, but it can help us save money when we're looking to expand out and drill new wells. So that's high productivity and low contacted volume. Now, tier 3, it gets a little weirder, right? So we have low productivity, but then we also have high contacted volume. And these wells typically could use something, some sort of operational guidance, whether it's a lateral cleanout, maybe some sort of acidizing. It could be something that we want to apply a refrac to kind of extend the fractures, clean them out. So there's opportunity here, because you know you've contacted the volume. You know if you let that well produce for the next billion years, you're eventually going to get it. But we want to accelerate those volumes. And so there's ways that we can get in there and try to get that oil or gas faster. So there's opportunity on those tier 3 wells. Tier 4 are the saddest of the well family. And so they're the lowest productivity, lowest contacted volume, but these could also be wells that we might want to look at for a refrac opportunity. A lot of refracs, not only will they increase the productivity around the wellbore, but you can extend the fractures out, contact more volume. So while it can be depressing a little bit to have tier 3 or tier 4 wells, what we know is there might be an economic case for intervention to improve those wells and get them up to a tier 1 or close to tier 1 level. So with the type curve areas that I would have, I'd be very interested in my great wells. And really, when I'm saying that the tier 4 wells weren't good, how do I know that? Well, I would compare them to the tier 1. Right? Because it's all judgments are made by how we associate wells to each other. And so when I would compare my wells to the tier 1s, that's when I would see, okay, maybe there's some opportunity here. We invest a little bit of money and we're going to get that back and more. Okay. Now here's something that is, it's a small thing, but it's important. Um, when we talk to our geologist friends, okay, when they talk about volume, they are typically talking about in-place volumes. As an RTA practitioner, like if you and I were talking on the phone, if you had a well, you wanted to talk it through with me, and we're having a chat, when I'm talking about volume, I'm going to be talking about contacted volume. RTA gives us a sense of what the contacted volume is, and contacted volume is always lower than in-place volumes. Now, this matters because the recovery factors we would calculate based on contacted volume will be a lot higher than what our geologist friends would calculate based on in-place volumes. And so when you're talking to other reservoir engineers and you're talking about contacted volume, that's great. But typically, if I was taking my messaging and I was either communicating to the geologist or the broader team or up the chain to the VP and up, I would recalculate the recovery factors to what they were accustomed to. And typically, people outside of the immediate reservoir engineering team think more in terms of in-place volumes. So this is a small thing, but communication of our results, I would argue, is just as important as getting the results themselves, because if we can't communicate it effectively, it's almost like, what's the point in doing it in the first place? So the language sounds very similar, but typically we're talking about two different things. So it's kind of, it's not a secret code, but it could be. When you're talking to me, contacted volume, that's what I'm thinking about. But external to that, we want to think about in-place volumes, particularly when we're calculating those recovery factors. Now, with RTA, people chase the perfect model match. Okay, this is the thing, and they want every point to be perfect and all the rest of it. Data isn't perfect, and so what we're really looking for is the general trends. And so I suggest to you is that we want to be roughly right. Like, we want to know that when we are thinking directionally, we're going in the right direction. And if we don't do that, we could be precisely wrong. And so what I don't want you to do is to lose heart. If you're given a data set that's really complicated to analyze, it's something that you just stick with the workflow we're going through this morning, go through that data, and just directionally see if you're moving in the right direction. Okay, so at this point, we're going to go into the software. If you're having any problems logging in, please let me know. Let me go back to my previous slide here where the password was, just to make sure that everybody has that available. Way back to the top. Oh, we're getting flashbacks from earlier today. Excellent. So let's go back here. So everyone, if you can log in, if you can go to courses.whitson.com, use the email address that you used to register, and use this password that you see on the screen right here. If you have a problem, please drop a message into chat. We have people online that can assist you. Or you can also email support@whitson.com. So I'll just give everybody a moment to log in. I will take a sip of coffee, and then we'll get started. Now, when you log in, you should see a field. Now, this field has a weird image on it. I grant you that. Okay, I went with Wizard of Oz. Maybe it's not my best work, but it's a movie. I liked the movie. I thought it was kind of funny. When you log into courses.whitson.com with your email and the password I showed on the screen a moment ago, you should see this field. If this is the first time you've opened Whitson, I want to just kind of give you a little sense of the environment before we dig in a little bit deeper. On the left-hand side, we have all of the different features in the software. We have fields, projects, wells, and scenarios. We're going to go through that really quickly and very soon. Beyond that, we can look at our production data, our PVT data, our bottom hole pressure data. And below that, we have a lot of the tools that we have available for you. We have decline curves, pressure normalized rate forecasts, the flowing material balance, analytical and numerical RTA. We have a numerical model, nodal analysis. We have bigger features like the forecast manager, auto forecasting, type well, group forecasting. We have a comparison plot, which is fantastic. We also have a multi-well numerical model, which is a lot of fun, and a multi-well gas lift optimization tool, amongst other well testing and other advanced PVT. So we have a lot of stuff on the left-hand side. Now let's scroll back up under fields. What I want you to know is a field is a logical grouping of wells. And in larger companies, different fields, different assets would have their own field. And typically the engineers for that asset or that field would be the only ones who had permission to view that. In other companies, it's just a way to keep everything logically separated, because different fields can have different equations of state. And an equation of state is basically the rules of thumb for the PVT for that region. And RTA, when we're analyzing a well, we need the production data, we need the bottom hole pressure data, but we also need the PVT data to understand how the fluids are acting with each other. And so having different fields is a great way to separate that out. Now, if everybody sees this field on their screen, you can click on my face if you want. And if you click on that, we'll open it up. And what we'll do is it'll bring you in to that field. Now, what I want you to know is that in every field, there is a main project. That main project is the repository for all of the data that your company has wired into Whitson Plus. And there's a lot of different ways to get data into Whitson. So what I consider main to be is kind of the buffet of wells that are available for me to analyze. Now, I can analyze the wells within main, but as we're going to do in a moment, I can also create my own projects. Projects are fantastic because I can keep it private just to myself. I could share it with some of my other teammates, or I can make it company-wide so everybody can see it. And so I can really change how I want what I'm working on to be viewed by my local team and the company as a whole. And so what we're going to do together is we're going to add a project. Now, before we do that, I want to touch on just two quick things. This is the hard refresh button that we have. So if you think something's not working exactly right, you press that button, it's going to do a hard refresh for you. This is our user manual. We'll use that a little bit later. The user manual is linked to whatever screen you're looking at. It's extremely helpful, and there's a lot of great information in there as well. The third thing is this is where you go for support. If you're in the software, you're having a challenge, you don't know where a button is or something's looking weird, you click on this button, you send it to us. And what it does is it sends us a link to the exact screen you're working on, and it allows us to kind of take a quick view, and then we can discuss with you what might be going on and help resolve your issue, okay? So let's add a project at the top right. So I'll go back one more. I was in fields. You find my project. I was in this field. I'm going to create a project. I'm going to go up to the top right and click Add Project. Now, when I click on that, it's going to open up a window, and I can name it whatever I want. I'm going to use my last name because it's easy. Name it whatever you'd like. And once you've entered a name, we want to click Save. Now, as soon as you create the project, Whitson opens you into that project. So if you notice on the left-hand side, we were in fields, we were in projects, and now we're right at the well level. Let's go back up a level. When I go back to projects, you can see the main says company-wide, but mine is private. I could change that if I wanted to share my project. I don't want to do it just yet, but these three dots on the side is the option to modify that. If I clicked on Edit Project, this is where I could change it. I could change it from private to restricted. Maybe I only want certain people to view it, or company-wide. And I'm going to leave it as private and close that down. So it's Add Project, enter whatever you'd like, usually your name, click Save, and you should find your project right here. Okay. All right. Now we have an empty project. It's kind of hard to do work on an empty project, right? We need some data. What we're going to do is we're going to use some data that's from the SPE Data Repository, which is a group of engineers. I'm associated with them. And what we were able to do is to get data donations from operators to have real data to work on, right? So it's been slightly sanitized, not too much, but it allows us to get a sense of that real data. And so this information is used a lot for universities for research, and we like to use it too here at Whitson. So what we want to do is we want to go up to Mass Upload. It's just to the top right. Click on Mass Upload, and you're going to see all of the different ways we can get information into Whitson. There's a lot of them. But what we want to do is to scroll all the way to the right. So I'm going to use this little arrow here, go all the way to the right. And I'm going to see something that says Examples. Let's click on that. Now, these are all the examples we have available, all those SPE Data Repository wells. What we care about is a subset of those wells. So if we scroll down, if we look here, what we're looking for is something that says RTA certificate wells. So right here, I'm going to scroll over. There's 3 wells in this well package, and we're going to click on Upload. Okay, so click on Upload, and that's going to take that data and place it into our project. Now, once it's done, I'm going to click the X here, and I should see the 3 wells here. Now, if you did those steps that I just did and you don't see the wells just yet, what you want to do is to refresh your browser, either by say hitting Control R or clicking the refresh button at the top right. And then as the wells get loaded, you should see them in your project. Let's give everybody a moment to do that. Click the refresh button if you don't see your wells. Okay. Now what we're going to do is we're going to analyze the kite well. So I'm going to come in here, I'm going to click on kite. As soon as I click on the well, you'll notice that on the left-hand side, it brings me down to scenarios. Now there's different ways we can use scenarios, okay? A scenario in itself is a copy of the well. A scenario, the only thing different scenarios need to have in common is the same raw data. So basically, you could run different analyses, different PVTs, different models, different everything. The only thing that needs to be the same is the production data, the raw data. So where it says scenarios right here, notice how it says main again. That's kind of a theme in our software. It's kind of the primary point is always known as the main. But let's create a scenario together. I'm going to click on Add New Scenario. So I'm just at the very top of my screen. I'm going to click on Add New Scenario. And I'm going to call this my base model. This is very typical for what I do for when I'm just trying to analyze the data and get my initial match. I always refer to it as my base model. Once my base model is done, I'll do something called a spaced model where I'll extend my fracture half lengths up to the maximum well spacing if it makes sense. And I will then create another forecast to kind of get a sense of the range of EURs for a system. So I like to use a base model, but notice this as well. Under access type, just like we had for projects, you can also have private scenarios and you can have company-wide scenarios. And so it can be private just to you, or it's one that you can share to everybody else at the company. Now, one thing that I would say to you is that within your team, I would highly suggest that you come up or agree to a naming convention for scenarios that are going to be used for different purposes. One of the problems that we can find is that different people working in different on different wells will have different naming conventions. And then when you're going to present whatever project you've been working on, understanding which version of which well that you need to bring together to show those results is a headache, and it can be a nightmare, frankly. So if you're doing an official version that's going to be used by your team, I would highly suggest that you come up with a set naming convention so that everybody's clear, for example, what a base model is. Everybody's clear what a space model is. If you did a model just for facilities to try to forecast what the total liquids will be for the next 3 months, have a name for that. Another positive of this is in the bigger companies, as things are growing, what we find is the global data teams want to come into the different assets and pull out those LFP numbers and those volume numbers and those EUR numbers. And it's easier for them if they know which scenario is the one that they should pull from, which is the official version, okay? So I've always started with base model. I'm going to leave mine as private, and I'm just going to click Save. And now at the top of the screen, you're going to notice the project. My project's called Ewert. This is the well, it's the kite well, and we're in a scenario called base model. We could create many more scenarios if we wanted. Now, in the scenarios module, we can see we have a lot of information available to us. On the right-hand side is all the metadata. This is stuff that people asked us just to kind of have available. They want to glance at it, they want to see it. But my eyes go more to the left-hand side of the screen. This is what I really care about. We talked about initial pressure. When we talked about initial pressure, we're talking about how RTA works by taking initial pressure and wellbore flowing pressure, and it's the difference of those two that gives the context for the rate, that gives us that productivity. And so initial pressure is an extremely important value to have. If we have a knowingness around initial pressure, we just have to understand that the results we get from RTA, that's going to widen the band of uncertainty that we're going to have. Now, what I want you to know is that if there's a default value in the software, it's going to present itself as blue text, right? So nothing strikes fear in my heart more than when I am analyzing a well for somebody and the default value for initial pressure is up at the top. And the default value is 8,000 PSI, just for your reference. And it's 8,000 PSI no matter what asset you're working on. It's just a software default. And so if you see a blue value, and this is a well that you really need to analyze and dig deep in, it's usually worth going and researching or asking the appropriate person what the value should be for that. And so in my case, I'm just using the default value for porosity. But we have our initial pressure here, we have our reservoir temperature here, and now we have height. Now there's two heights that we can have. We can have fracture height and we can have reservoir height. I typically keep those the same, unless there's microseismic or some other reason to change it, okay? So you can see the values are the same in our example here. Why do you care about height? One of the things that we're going to get from RTA, as we talked about, is volume, okay? When we sense the volume from a well, it is a shapeless blob of volume. We need to make three-dimensional sense of this blob by stuffing it into a rectangle, right? That's the depth of that rectangle is the height, and the width of it is going to be the lateral length, right? And so the only way we can squish it down is if there's enough room for it is by extending those fracture half lengths out. So what I'm saying to you is that if your height is too low, the fracture half lengths you're going to get computed from the software are going to be way too big, right? You put a height of 1 foot in there, you're going to have 4,000 or 5,000 foot fracture half lengths. Conversely, if your height is way too tall, if you think your height is 1,000 feet and it's not, your fracture half lengths are going to come back saying that, you know, your fracture half lengths are only about 5 feet or maybe less. And we care about this because when we're thinking of fracture half length minimums, the average fracture half length through our system, that goes directly into how many wells per section we should probably put in. And so if your height is wildly wrong, you can miss what the optimal well spacing would be for your upcoming wells. And so height is very important, and porosity plays into that as well. Porosity and height kind of work the same way, where if it's too high or too low, it's going to modify that fracture half length, and that's why you care about it so much. Now underneath this, we have something called number of fractures. Number of fractures is important, but it's not important. You know, how does that make sense? Let me explain it. Okay. It doesn't really matter to me necessarily what your number of fractures are, but it's important to understand how it changes your analysis. Number of fractures, when you increase your number of fractures, what this means is the permeability that you'll get from the software will be lower. Okay, so if I put 2,000 fractures in, my permeability would result to something like 0.01 nanodarcies. Or if I put my number of fractures at 10, the permeability would probably come out in the microdarcy range. Okay, so how do we get around this? Well, very typically, people aren't sure what their permeability is for their system. They have a range, but it's usually a pretty big range. So my advice to you for number of fractures is that however you calculate it, make sure you use it the same way for all the wells in your type curve area, or all the wells that you have that you're analyzing with RTA and Whitson. Now, there's different strategies here. Some companies will use number of stages as their number of fractures. Other companies will use number of stages times number of clusters. That usually gives you a really high number of fractures. So what we typically see is that people will use number of stages times number of clusters times an efficiency factor. And this, it changes a little bit, but usually what we see is it's usually 50% or 60%. So do I care whether you use 50 or 60%? No. All I'm asking is that you apply it the same way every time you're analyzing a well. Because what we're trying to do, especially if you're analyzing a pad of wells, what you would hope to see is that the permeabilities that you get from analyzing those pads of that pad of wells is very similar, right? We wouldn't expect wells that were drilled and completed the same way to have really different permeabilities. But if you've changed how you've input your number of fractures into each of those 4 wells in the pad, you're not going to resolve it down to the same permeability. It's going to be all over the map. So with number of fractures, just whatever way you and your team decide to do it, just make sure you're consistent. That's going to help you in the long run when you're doing well comparisons. Under that, we have water saturation. Usually this is another number we also get from our geologist friends. Under that is compressibility. Now I'm going to ask you to add a value in here, and I'm going to touch on it later. So I just need you to trust me, and we'll get there kind of near the end of the morning. But we're going to have to add a gamma, okay? A gamma is something we use for overpressured reservoirs. Now, how do I know this well is overpressured? Go over here to where it says TVD. We have a calculator here. Let's click on that calculator. And what that's going to do is it's going to pull in that TVD value at the heel of our well. Now I could type in a value if I had a down dip well and I wanted a different point on the lateral, but this pulls that first value in. And if I scroll down, notice how the bottom here we have something called pressure gradient. I care very much what the pressure gradient of my well is. The reason I care about pressure gradient is if it's overpressured, I need to start thinking about something we call gamma. Gamma is a correction that modifies how effective the permeability is as you deplete your reservoir. And so what it's trying to mimic, what it's trying to model is if you think about it, if you're a reservoir and you have really bloated pores and you start producing that, those pores are going to start to shrink. And as they shrink, that overburden pressure is going to start to take over more and more. And as that overburden pressure starts to take over more and more, a lot of the pathways that we had for fluid flow are going to be cut off or compromised. And so what's essentially happening is the effective permeability when we start producing is going to go down over time. And so gamma is a way of compensating for that. Now we have different strategies to come up with specific values for that. There's a plot that I'll show you when we get to the numerical model, which will show you kind of how that permeability changes. But what I'll ask you to do right now, where it says matrix gamma, let's put in a 2. 2 is a pretty good number. Under fracture gamma, let's put a 2. Okay, just trust me. We'll get there. I'll show you the plot. It'll make more sense when we get to the model. So we're here, we're in scenarios. We've talked about all of the inputs that help us make physical space sense of the results that we're going to get from RTA. And what we've done is we've added a gamma here of 2 for matrix and 2 for gamma. Now we'll touch on production data, and then we're going to take a 10-minute break. But production data, this is where all of your data gets loaded into, okay? Now you can see this data is a little messy, right? This is kind of the way it looks with a lot of wells that we see. When I look at production data, when I'm doing an RT analysis, there's really only, maybe there's a couple things that I look out for. First, I want a general sense of the noisiness of my data. I would consider this noisy, right? The smooth pressures, the smooth rates is really what you would love to see. Very rarely do we get them. So I'm getting a general sense that I'm getting some noise. Okay. But the second thing you care about when you look at your raw production data is anywhere there's a gap. When there is a gap in production, it can either be because some piece of equipment like an ESP or something went down, or it could be because there was a shut-in and you were going to get frac hit, or maybe there was a lateral cleanout or an acidizing or a refrac or something took place. What I'm saying to you is whenever there is a gap in your data, be suspicious. Because what we don't know, if you have the well history near you, that's a good thing to have. But typically when I'm analyzing a well, I don't know what happened there. Usually if there's a high water signature that happens right afterwards, that gives me some idea it's probably a frac hit, sometimes a recompletion. But the reason you care about that is when you're analyzing a well, we want to analyze the well in its purest form. And so if we have a well that was online for, let's say, 2 years, and it was uninterrupted, and we have quality data, we can analyze that. But then let's say that that same well was shut in for a few weeks and it was frac hit. And let's say that frac hit negatively affected our well. Let's say it pushed a bunch of sand and garbage into our lateral. Well, the data after that shut in, the numerical model won't be able to match it. What the numerical model will do is tell us what we should have gotten versus what we got. So we can quantify the difference to see if it makes economic sense going in and doing some sort of operational thing in order to clean out that well or fix whatever happened. So when there's a gap in the data, our spidey sense starts to signal to say, okay, did something meaningfully change? Did the well change or did it go back on its previous trend? And we're going to use a type curve in order to identify that soon after the break. So when we come back, we're going to jump into PVT and bottom hole pressure, and we're going to start more into the workflow that we talked about before. I'll put a timer on the screen for about 10 minutes in just a moment here, and then we'll come back and we'll continue on. So please take 10 minutes, grab some coffee or tea, some water perhaps, and we'll be back here really soon.
Well, the slides done rolled on by, and the clock is nodding slow. In the Whitson course room glow, rate transient analysis on the go. You've been watching every curve, every dip and every sign. Now it's coffee for the mind, time to lay that burden down. If you need a little help, don't keep it to yourself. You know where to send it off and let that worry drift on by. It's break time now, my friend. Take a little breath again. Break time now, my friend. We'll pick it up when breaks come in. If you've got a question, send it through support@whitson.com, or type it in the Teams chat too. That's the place to lean on through. When you come back, we'll carry on with the next part of the road. Same old screen, same steady load, learning what the numbers show. Ain't no rush and ain't no race, just a little pause between. Let your thoughts unclench and rest, then we'll meet back in the stream. If you need a little help, don't keep it to yourself. You know where to send it off and let that worry drift on by. It's break time now, my friend. Take a little breath again. Break time now, my friend. We'll pick it up when breaks come in. If you've got a question, send it through support@whitson.com, or type it in the Teams chat too. That's the place to lean on through. Set your cup down slow, stretch your boots out wide. You've done a good job so far, let that honest effort ride. It's break time now, my friend. Take a little breath again. Break time now, my friend. We'll pick it up when breaks come in. If you've got a question, send it through support@whitson.com, or type it in the Teams chat too. That's the place to lean on through.
Well, the screen went still and the coffee's gone cold. We've been learning all morning, now the nerves can unfold. Rate transient analysis got us thinking all day, but the clock says pause, darling, we can breathe forward. for a spell. Lay your notes right down, ease that furrowed brow. We'll take a little rest here and come back around. It's break time in the Whitson course. Set your hands down easy, let the minutes drift across. It's break time, don't you fret no more. We'll be back in a moment, then we'll ride that learning tour. If you've got a hard question, don't you keep it in. Send it off to support@whitson.com, let the help roll in. Or type it in the team's chat, let it ring through the wire. There's a hand on the wheel now, keeping things on fire. No need to rush it, no need to guess. We'll catch every answer and do the rest. It's break time in the Whitson course. Set your hands down easy, let the minutes drift across. It's break time, don't you fret no more. We'll be back in a moment, then we'll ride that learning tour. Take a breath, let it settle, watch that worry fade. We'll return with fresh eyes and a little more gray. Yeah, the day keeps moving, but the pause feels right. One good rest can make a hard thing a whole lot lighter tonight. It's break time in the Whitson course. Set your hands down easy, let the minutes drift across. It's break time, don't you fret no more. We'll be back in a moment, then we'll ride that learning tour.
Logging, leaning, you made it this far. Screens full of numbers and charts to spot. Take a quick breath, let your shoulders drop. We've been running the flags, now the clock says stop. So grab your tea or just stretch out. The next few minutes are yours, no doubt. Got one question, don't let it hide. It's break time in Whitson. Today's break time. Let the noise fade away. It's break time. Virtual course, alright. Come back refreshed and we'll take on the night. If you need a hand or you got stuck, send support. No, don't wait, don't luck. Support@whitson.com. That line still shines. Or drop your question in the team's chat line. Keep it moving, keep it clear. We'll meet right back when the break is near. Got one question, don't let it hide. It's break time in Whitson. Today's break time. Let the noise fade away. It's break time. Virtual course, alright. Come back refreshed and we'll take on the night.
There we go. A little music for the break time there. Welcome back. Aiden, I saw your question. It's a great question. Okay, so for those of you that didn't see it in chat, Aiden said, should frac height equal reservoir height? For example, if our reservoir is 100 feet, but the frac height is assumed to be 200 feet and only 100 feet is productive, what should be done? You should use 100 feet. right? Now, it depends. Now, in the other parts of the height, are you getting water? Are you getting anything else? If you're getting nothing, then 100 feet is fine. But if the other 100 feet on top of that has water production, and we're trying to match that, we need to make sure we take into account that volume as well. Now, this can get really kind of complicated if we have two different layers with two different permeabilities and all the rest of it. So it might be a slightly different discussion. But based on the way that you asked the question, my recommendation would be to use 100 feet. Okay, let's share my screen again. We're all refreshed. Oh yeah, but we were looking at data kind of like this. Okay, I remember. Right? So what we've covered so far is we kind of went through Whitson. We talked about fields, projects, wells, and scenarios. We made a custom scenario. We kept it private just because we want to work on it ourselves. And then we were looking at the production data, and we know that we can't get a lot of value out of this necessarily. I mean, it's good to, you can look at your GORs and your WORs. There's a lot of different things we can do with the plots. You can squish them down. If I just want to look at gas, for example, I can just double click on gas. I can double click again to bring everything back. And this is actually something that's important to understand. With all of the plots in Whitson, you can interact with them. But if you go up to the top right, you'll see 3 dots there. And what you can do is you can actually export that out. You can go to Image, Excel, PowerPoint, which is awesome, and other images as well. And so any of the plots that you see in Whitson, if you're interested in looking at that raw data, or you want to take that image and you need it for a presentation or for a project you're working on, we make that exceedingly simple. And it's a really great feature of the software. So we're on production data. Now, also, Aidan, let me know if that answered your question, okay? We looked at the production data, but now we need to go to PVT. PVT is extremely important to us when we're doing RTA. We want to know how these fluids are interacting together. Now, for this case, what we're looking at is an oil well. And so what I want you to know is that when we have an equation of state for the region that we're interested in, and Whitson comes with a default, and that's the one we'll be using this morning, all we need to do to generate the PVT table, all of those complex things that we have, when we have an equation of state, is to use the GOR. It's fantastic. It's extremely convenient. So when you click on PVT on the left-hand side here, these we call tiles, okay? Now I'm going to open up this tile on the left-hand side. Now when I click on this, I'm going to get a screen that pops up. This screen allows me to tune the GOR. So I could take this line and I could move it up. And when I do that, you'll see my initial GOR, the value goes up as well, or I could move it down. And what we're looking for is what we think that initial GOR is. And so where it was initially is where we want it to be. So I'm going to type this in. 750 is where we want it to be. Now, to improve on this, if you happen to have an API gravity, you can pair the GOR, initial GOR you've selected with an API gravity. Fantastic. Even better, if you have a saturation pressure, you can take that GOR, tune it, and add that saturation pressure as well. And so if you have that additional information, that can always help, but really at the very baseline of what we require is a GOR. Now I'll make sure that 750 is what's down here, and I'm going to click Save. Now when I click Save, what the software is going to do is it's going to create a custom phase envelope for me. And you can see it right here. And once again, this is another plot that I can interact with. I can export out. I can do all of those things with it. But let's click on PVT table at the very top. What the equation of state actually did for me is it generated all of these relationships that I care about. The relationship of oil and gas, right? They're almost like family members. And the equation of state is kind of like the rules of how this family interacts with each other. And so it's super important. It allows us to kind of view the system from different fluid perspectives, but it generates all of that for me right away, which is absolutely fantastic. We have different equation of state models. We have custom ones for different assets. If you're working in an asset and you're interested whether we have an equation of state model we've developed for that, reach out to us and ask us. And if we do, we can talk to you about engaging that in your software. Once we have our PVT, the next big thing is bottom hole pressure. And this is a big one. So let's click on bottom hole pressure. So when we looked at those equations earlier, it was PI and PWF, right? And PWF is the wellbore flowing pressure for the bottom of the wellbore. And typically what we have is we have wellhead pressures, tubing pressures, casing pressures. And so what we have to do is we have to translate those wellhead pressures down to the sand face in order to use the RTA equations that we have. And so that's why we need to calculate bottom hole pressures. Now, there's a lot of different ways to set up your wellbore configuration. We accept a lot of different configurations through time. Let's look at that right now. Here where it says well data, this is another tile. Let's click on this box at the top right. When we do this, we're open with an initial screen. And what this initial screen is showing you is where the perforations are for the lateral, but it also has the information on the deviation survey. Now we can view the well trajectory from this, and usually I'll click on this because I want to know if it's an up dip well or a down dip well, and really it doesn't mean a whole lot to me unless I see the horizontal wellbore like really kick up or really kick down further out. Something like this, yes, it's going up a little bit, but it's really not going to meaningfully change my analysis very much. But it's very easy to see that and get a view of that from the software. When I click on well data, this is where we can really get into things. You can see we have two configurations. One was flowing up tubing, the next was gas lift. We can have jet pump, gas lift, ESP, rod pump, plunger lift. When it comes to gas lift, you can put in your own valve information. We can try to calculate the valve information for you using automatic. There's a lot of great features here. With ESPs, we can use custom values to really tune it to the system that you're using. A lot of great stuff in here. I believe there's actually a course just on bottom hole pressures. So for our purposes, for RTA, I think that's good. But what we want to do is click Save. When I click on the button at the top that says Calculate Sand Face Pressures, what it's going to do, what the software is going to do, is it's actually going to calculate all of these correlations for me. Now, we're going to use the gauge pressure. It's not really a gauge pressure, but it's the bottom hole pressure that was given to the committee when we received this data from the data donor, from the operator. And so we're going to stick with that. But what I want you to know is that we have Beggs and Brill, Hagedorn and Brown, Waldesmeid and Gahar, and Gray. We typically recommend Waldesmeid and Gahar. We did an in-depth analysis with various operators. We looked at different GOR profiles, different assets. And we found that Waldesmeid and Gahar was really the one that worked the best in most, if not all of those situations. And so that's the default that I use, is Waldesmeid and Gahar. But for the purposes today, what we'll do is we're just going to stick at the very top where it says gauge, okay? So we have PVT, simple to do. We have our bottom hole pressure, simple to do. Now we can start digging in and trying to figure out, from the RTA perspective, what we're actually dealing with. And so the first thing that we're going to do in the form of interpretation is we're going to go to the flowing material balance. So let's go down here. Actually, you know what? I'm going to switch it up on you. Let's go to Analytical RTA. Let's click on Analytical RTA. Now, the reason I want to go to Analytical RTA first is, remember, flowing material balance, the purpose of it is to give me my contacted volume. But my preference is that I want to know what the flow regime is before I see that volume. I want to know the context for the volume that I'm going to get. I want to know whether I'm in bounded flow. I want to know if I'm in linear flow. And I want to know if I'm in transitional flow. And so under Analytical RTA, we have three different selections here. There's classical, which is the square root time plot. We have fractional, and we also have the type curve. Let's click on type curve here. I'm going to take a pause here and bring up my slides once again. I have to zip through a bunch here. I hope I'm not going to give anyone motion sickness. Zip through. Might be a faster way to do this, but I'm just going to do it the old tried and true method. Okay. There's something in the software, you'll notice you see analytical and you see numerical. These are two words that are popping up regularly. I want to be very clear as to what we're talking about here. When I say analytical to you within the context of the software, I'm talking about a method that is single phase. Okay, now it's single phase, it's using equations, we're trying to figure out what's going on. But the reason you care that it's single phase is, like, we're going to be looking at oil. Oil has no idea what gas is doing. It has no idea what water's doing. And so there's signatures that we typically see when we have a GOR spike or when we have flowback water in early time. And so when we're talking about analytical, we're looking at the system through the lens of only a single fluid. And this fluid is telling us a story between what its experience was and what the PI minus PWF was. So what the drawdown was and what it was experiencing. When I say numerical to you, what I'm talking about is a numerical method. I'm talking about something that can handle multi-phase effects. And so in terms of numerical methods, we're taking into account the oil, the gas, the water. So it's all together. And so a question you might ask is, well, why would we ever bother with an analytical method if the numerical methods are there? And the answer to that is that analytical methods give us a lot of value from a qualitative interpretation. Now, when I say qualitative, what I'm suggesting to you is that the numbers don't matter, but the shapes do. And I know as engineers, we care very much about numbers. It's kind of what we're known for. I don't like a fracture half-length unless there's a third decimal place. I'm kidding. But analytical and the shapes of it can really give us deep insights. And it's a part of the history of RTA. It's nothing to be abandoned because we're moving more to more computational methods and more numerical methods and everything's getting faster. The fundamentals still hold true. And what I'm going to show you of how I use analytical RTA brings me value to every single well that I analyze. Okay, so that's the difference between analytical and numerical. Now, analytical does have its drawbacks, and we were aware of this when this was the only way to interpret wells a number of years ago. In terms of oil, we're going to see that we can identify linear flow and bounded flow. Okay, with oil, the tricky part always was that if your GOR profile changed, the oil would present itself as being in bounded flow when maybe it wasn't in bounded flow. And so we knew that when we used these methods and cared about the numbers, which I'm suggesting to I wouldn't anymore, I care more about the shapes, we knew that would be a conservative estimate for that contacted volume. Now for gas, it gets a little trickier. For gas, if you have a system that's just gas and water, let's say, you could say, well, why would I need to use anything numerical or multi-phase? It's gas and it's water. It's not a big deal. Well, with analytical methods, what we need to do in order to get gas to work with how those equations were developed, and those equations were developed for a constant rate system, single phase, constant compressibility, very simplified. Gas is many things, but it is not constant compressibility. The compressibility of gas is wild. It reminds me of my 6-year-old. Like it's just give them some sugar and it just takes right off, right? If you think about that curve of the compressibility of gas, it changes a lot. And so in order to convert gas into a way that we can use it in analytical RTA, we need to do two things. The first thing is a pseudo pressure correction. That's not a problem. Pseudo pressure, it's an exact calculation. There's no problem with that. The challenge comes with something called pseudo time. Pseudo time is trying to figure out what the contacted volume is, so we can get a sense of what the average reservoir pressure is, so that we can get a sense of what the average compressibility of gas is at every time step through the history. Now, sometimes this works well, but other times there's some challenges with it. Now, what makes it challenging is if you have a system, the lower the permeability of your system, the more fractures you have in your system, and the more overpressured it is, it's harder to understand what that compressibility is at a given point in time. And what does this mean? It means that when you're analyzing gas data, and if you were to use the numbers from analytical RTA, you would either really overestimate the size of your volume when it comes to gas, or you would drastically underestimate it. And so years ago, when we, once again, just had analytical methods before we went to a numerical model, we knew that the volumes might switch a little bit when we move from that analytical pseudo-time space into the numerical space. And so what I'm saying to you is that numerical methods don't require that pseudo-time correction. And so even if you're doing this for gas and you're going to use RTA for gas, we're going to use those analytical methods for qualitative analysis, but I would still deeply recommend that you go through that numerical RTA, flowing material balance, and numerical model to get the best values, the most consistent values from your data. Now, one of the things you're going to notice as we go through analytical RTA is on the x-axis, you're going to see material balance time. It's going to say MBT. And so superposition is a way that we use that data. I mentioned it earlier this morning where with material balance time, it takes variable rate data and makes it equivalent constant rate. But what it also does is it sorts the reservoir signal for us. It's kind of weird. When you think of superposition, and there's various types of superposition. There's superposition for linear flow, radial flow, bilinear flow, boundary dominated flow. What we really care about is superposition for linear flow and boundary dominated flow. Okay, and that's material balance time. What we need to understand about superposition, and I don't want to give anybody nightmares. It's later in the morning, so I think we're okay. Superposition time isn't chronological time, okay? And the way I think about it, it gives me the heebie-jeebies, but this is the way I think about it, is it's a little bit like Laplace transforms. Ugh. And none of us, I mean, some of us might like Laplace transforms. There's no judgment if you like them. It scares me a little bit. But if you remember back in the day when we would be doing the math for Laplace transforms, you would have this equation, which was just crazy, right? And you would convert it into like S space or whatever we called it. And then you would just add those two things together, and then you'd reconvert it back. What I'm saying to you is that material balance time is kind of like that Laplace space because you're stepping out of chronological time. You're into a system that is sorting the data by its reservoir signal. And so when you're looking at a plot, because you have a point over to the left and you have a point over to the right, that doesn't mean that chronologically that's how it happened. In fact, you'll see that the points kind of bounce back and forth if you were to view them in real time. But material balance time is something we require. It helps us understand that reservoir signal. And the way that I think about it is really what we're doing is we're superposing two reservoir signals together. Remember that reservoir signal is the building block that we're interested in. And so if I want to create a variable rate signature using constant rate data, if I have constant rate right here, I can add it to itself. And then the pressure, where the original pressure would have continued on like this, I can then subtract and see what the new pressure would give it. And when I add things together or subtract them away, we can make very complex shapes out of something very simple. Now, when this was explained to me back at Phuket a long time ago, I struggled with superposition. I understood what people were trying to tell me, but I didn't get it. You know what I mean? Like I didn't have a feel for it, I guess is the better way to go. And the way that I got over this was kind of unconventional. After a number of months at Phuket, I needed a break. Okay, I needed a break. So what I did was I booked myself a trip to Las Vegas, as a young man would do. And so I went to Las Vegas, and I won't say exactly what time of the night or morning this was, but I was between the Bellagio and the Aria. And off in the distance, I saw some sort of statue, and I thought it was really interesting. And so as I approached it, what I realized was that it was a Statue of Liberty. And I like the Statue of Liberty. I think it's fantastic. But on closer inspection, what was really interesting was that the Statue of Liberty, someone had taken the time to build it out of individual Lego blocks. Now, I understand there's probably different shaped Lego blocks, but stick with me. Let's pretend they're all the one simple shape. And as I stood there trying to figure out how long it took to make this, it was like 7 or 8 feet tall, Statue of Liberty out of Lego blocks, I realized that I was looking at an example of superposition. Now, we could say that they put the blocks together. They made the shapes all together. But if we wanted to be really maybe elitist, we could say, well, they superposed them. And that's exactly what they did. So what I'm saying to you, when we're looking at variable rate data, and our production data is all over the place and it's messy, that reservoir signal, when it's added and subtracted from itself, can take a simple concept, a simple shape, that reservoir signal, and build complex shapes. And superposition helps us do that, okay? So we're going to talk about the type curve first of all. Now, I'm talking about a type curve, not a type well, okay? I will say type curve when I'm talking to people when I know they mean type well, but we're pretty specific internally about the difference, right? A type well is when you have the analogous wells, you're trying to come up with a P10, P50, P90 for a region. A type curve is essentially a model in and of itself where it's going to model, it's kind of a pre-run model of idealized reservoir signal that lets us know kind of what true data quality would look like. So let me go back one here. We have the Fekovich type curve, Blasingame, and Agarwal. I like the Agarwal. That's the one that I typically use, but I'll use the Blasingame as well. Fekovich really depends kind of on the data quality that you have. So if you have nice, smooth data, I find Fekovich to be valuable. But typically my go-to is the Agarwal. So let's go back to the software here. So I'm in Analytical RTA, and I'm at the type curve here. Okay. Now I'm going to expand my window. So I'm going to expand this out just so it's clearer to see. What you are looking at is idealized reservoir signal. Each of these different stems is a different form of transient flow. We could think of it simply as linear flow with different levels of skin, okay? That's mostly true. On the right-hand side is boundary-dominated flow. And so the first question we have, when you have a data set and you know you're going to go analyze it, the first question you need to ask yourself is there reservoir signal present in the data? If there's not, there's not much reason to go on, right, with RTA, because you're going to try to listen to the reservoir signal, it's all going to be muddled. So the first question we have is, do we believe we have reservoir signal? So it doesn't really matter exactly where I place this data. You see the numbers over here? I don't care about those numbers. These numbers are being calculated for a vertical well in a cylindrical reservoir. That's not the system we have. We have a horizontal multifrac well in the rectangular reservoir. And so these numbers, the math is for something else. We just care about the shapes. And so the first thing I do is I move my data, and I start at the top left, and I move it down, and I just want to place it pretty close to where the idealized reservoir signal is. And so the question I'm asking myself is, do I have reservoir signal? This portion of the data is overlying my idealized curve. I do. And so I should continue. The second question I have is, what flow regime or flow regimes do I think I have? This tells me I have some linear. This might be transitional or boundary, but it seems like I've got some linear and some boundary dominated flow. We have another tool we'll talk about in a moment that will help us with that. But this plot does two other things that is really helpful for us. One is it's a great place to filter your data. Filtering doesn't delete the data. It doesn't remove it. It just removes it from our site, okay? Because we want to focus on certain trends. Now, when I said, in terms of data quality or how the well is doing, you don't have to click with me. I'm just going to click back to production data. It'd be very difficult to look at this data and say that there's reservoir signal. To me, it's impossible to tell. And so what Analytical RTA, the type curve specifically does for us is it translates that in a way so we can get a view of what's going on. Now, I told you when we looked at production data that we care if there's gaps. The gaps are spidey sense tingles. We want to know whether something changed. We can see that in the type curve, okay? So first of all, let's talk about this downwards trend that we're seeing in the early time portion of the data. That is the classic signal when flowback water is dominating the pressure or the drawdown. So it's very typical to see what we could consider to be a skin, but it's very temporary, and then it comes back on trend, okay? So that's something that we look out for. So we're going to want to filter those points out in just a moment. But if there had been a shut-in in this data, what would happen is after the shut-in was complete, you would get a tail of data points that would start up here, and it would either come back down on trend, and if it came back to the previous trend, that means that we were kind of poked, we were kind of perturbed, but we just kept on living our life the way we were before. But if this was like a parent well, pardon me, and a child well came on next to me, and I had reserves reallocation, like I was losing volume to it, what would happen is these data points would be up here, they would come down, and then they would go below my previous trend. When it goes below, that shows that we've lost volume. Now, I have seen positive frac hits. It doesn't happen all the time, but with a positive frac hit, you'd see the same curl come up, and the data would go above the previous trend. And that tells us that we increased in volume. What's really great is if you ever have a refrac well, it's really cool to see because you'll see the previous trend, and then the refrac data will be kind of floating up here, showing us that increased in productivity and in volume. And so this is a great way to get a snapshot of your well's history. And what you're going to do with that snapshot of the well's history is you're going to understand whether or not you should expect a model to match through the entire history of your well, or just one part of it or another part of it. If this well had been frac hit and the reserves reallocation was happening, I would match my model before that happened. I'd have a scenario of before, and then I would have a scenario after. Because what I want to understand is, what am I losing? What was I going to get, and what am I going to get now? And then I would cross-reference that with the child well to see whether or not it was really economic, taking into account what it stole from my parent well. So this is a great way to understand the data in just a snapshot, okay? So I'm going to filter the data. Just up here, we have the spray tool. I love the spray tool. I'm going to exclude some data here. Now, what I like about the spray tool is I have a scroll wheel on my mouse here, and I can make it big and small, okay? Filtering data is fun. Okay, I'm going to use my left button. I'm going to remove the data points here. There are two different ways. I'm sure there's more, but let's stick with two that you could filter your data, okay? One is that you're just going to remove points which you have lower confidence in and let the data that has reservoir signal remain. But I've also seen it where people try to take a mess of data, like a cloud of data points, and try to carve it down to kind of carve out a reservoir signal. And that is something where the well's not really telling you something, you're trying to impose your will on it, okay? And this kind of reminds me It reminds me when I was 14. I was 14 or 15. If you remember, years ago, it depends. I don't know the age range of everyone that's here, but hopefully we remember the movie Speed when it came out. That was really cool. Speed, it had Keanu Reeves. Keanu Reeves was always really cool in the 90s. And when that movie came out, I lived in a small town in northern Canada. And when you live in a small town, you always want to be cool. I was strove. I didn't quite make it, but that's okay. We can have that discussion another time. But my brother decided that he really wanted Keanu Reeves's haircut. He thought it was totally cool, and a lot of us thought it was really cool. And my brother's a very smart guy, but he had a lapse in judgment. He really did. So he went to the Shoppers Drug Mart, which is this basically a CVS in Canada, and he came home with some electronic well clippers. And I don't know what neurons connected where he thought that he could bring this home, give it to me. And his request was, can you give me the Keanu Reeves haircut? So I'm a teenager with no background in cutting hair whatsoever, never held clippers in my life. Of course, my answer was, of course. So I grabbed the clippers and I start working on this, right? And I have to tell you, when I started, it was looking really good. I was actually really pleased with myself. And so I took a little bit off and a little bit more and a little bit more. And I was really close to what I think my brother was looking for. But of course, I couldn't leave well enough alone. And we all know where this story's going. When my parents got home and saw my brother with no hair, they were really freaked out. And I think I got in trouble for it, which seems really bizarre to me. Once again, another story. But I tell you that story to say that filtering data is like giving your brother a haircut, where you need just a little bit off at the time. When people get really kind of gregarious with their filtering, you could go in here and try to really carve out a perfect signal, right? But is that real? Well, no, because you're removing so much stuff that you're just trying to kind of carve out just a little bit that you like. We need to let the well communicate to us what is actually going on. I'm just going to reset my filtering here. I'm going to re-exclude these early points here. And so less is more. We want to be very methodical of how we filter the data. We're not trying to carve out a fake reservoir signal out of the data we've been presented with. We're trying to let the existing reservoir signal come out of the noise. And so this early time data I've removed, these points over here offend me, so I'm going to get rid of these two. I may have taken a few too many off, but I'll leave it there. So yes, we have reservoir signal. We have a continuous set of data steps. We don't have any discontinuities. So we know that we should be able to get a model match that works all the way through the data. And so that's what we get from the type curve. The next thing we want to do is go to fractional RTA, which is a fantastic tool. So let's click on fractional RTA. Now the filtering we did has persisted, which is awesome. Now, fractional RTA was developed by Jorge Acuna at his time at Chevron, and it was originally done for fracture clustering, and there's value there. But what's interesting is when people develop tools, you can use them in different ways or ways that maybe they weren't considered to be used before. And so on your screen at the top left in the numbers that you see, you're going to see a delta value. That's the value we really care about. What I want you to know is if there's a delta of 1, that indicates radial flow. Okay, we're not going to see that very often. A delta of 0.75 would be bilinear flow. If your delta is between 0.5 and 0.75, and for my folks that have a lot of gas wells, this is really important. That's when you will see if there's a skin associated with your data. We call it dimensionless fracture conductivity, but it means there's a productivity loss at that well. If your delta is exactly 0.5, that's linear flow. That's a great time. And if it's between 0 and 0.5, that's transitional flow. So that means you've probably hit most of your volume, but you're probably going to get a little bit more. How much more? We don't know. But we can run the model at different spacings, different XFs, to kind of try to feel that out a little bit. And finally, if your delta is at 0, that means you're in boundary dominated flow. Now, what's really great is if I go up to the help file right here, the user manual, just at the top right, I'm going to scroll down. I think it's near the bottom here. I'm going to scroll, bring it down. Here's the table, okay? I took a screenshot of this. I printed it out. I have it at my desk all the time. I like to refer to it. I mean, I probably have it memorized, but I always like to look at a piece of paper. It makes me think it's more scientific. But this is a really great reference to have, okay? So I believe everyone will have access to the slides, so it will be there as well. But this is a really great reference hidden in our help file. And so what I'm saying to you is that the delta on the left-hand side translates to the slope of the analysis line. And you can manually move the analysis line. You can move it to try to match the data yourself. We also have a fit option. And so we have the lasso here. I can click on that. Once again, a spray gun. This isn't going to filter the data. It's going to help us with our line fit. You see something like that. The way that I use this is I will type in 0.5. So I'm going to type in 0.5, and it's going to give me the slope for linear flow, and I like to place it over my data, something like that. And what this is telling me is I do have like a portion of my well history that has linear flow, which is fantastic. The next thing I'll do is I'll either match the line manually, or what I do is I type in a 0 for the delta. Now remember, 0 is boundary dominated flow. And so when I type in a 0, it's going to change the slope, and I'm then going to try to match it over the rest of my data. So what I really care about is what flow regimes do I have? Now, the fact that I have boundary dominated flow is very significant to me, because that means when I go to my flowing material balance, that means that the flowing material balance, the volume that I get from that, is really what this well is going to see. If I was in linear flow, I would consider what I get from flowing material balance, the volume that I get, to be a pretty conservative estimate. But we're in bounded flow. So this well has seen what it's seen. Unless it gets perturbed or the reserves get taken away from a child well or an infill, we should have a pretty good set on what this well is capable of producing over the rest of its life. Now, finally, we have classical. Classical is still used, although a lot of times numerical RTA is kind of the go-to, but let's talk about classical. Okay, so I'm looking at the top left plot that we have. This was the way that we analyzed unconventional wells for many years before numerical RTA kind of got a foothold in how we do things now. And so out of all of the analytical RTA plots, this is probably the one that I use the least. I always use type curve. I always use fractional. Sometimes I'll use the square root time plot. What I want you to know is that it's called a square root time plot because if you have data that is in linear flow, it presents itself as a straight line on a square root time plot. So if you see a straight line character on your data, that is linear flow. The next thing we need to understand is if you're in transition or bounded flow, you'll get an upwards curvature, okay? So now if I have two wells and they have two different straight lines, the slope of that line is very meaningful to me. The flatter the line, the better the well. The flatter the data presents itself, the higher the LFP. Now, LFP is an interesting value. That's the value we use for productivity. Now, if I'm analyzing wells in the Bakken and you're in the Marcellus and we're at a conference, and I announce to you that I have a well that has an LFP of over 1 million, that doesn't mean anything to you, okay? Because the LFP is dependent on different assets, different fluids. And so comparing them really makes more sense when we're comparing wells within a type curve area or type curve areas that are similar in terms of fluid to each other. And so LFP is a great value for a point of comparison. And what I'm saying is if you sent me a pad of wells and we were going to work through them together, I'd be really interested to see how they showed up on a square root time plot to see if one was really flat and one was more vertical, had more of a vertical line to it, because I'd want to know why that vertical line well wasn't acting the way that we expected to. So this is a really great way to do that quick comparison. So the slope of the line, the analysis line, very meaningful to us. There's sometimes with our data, if we have a skin, if there's a dimensionless fracture conductivity loss, which we would have seen in fractional RTA for this example, that presents itself on a square root time plot as a positive y-intercept. A positive y-intercept is a bad thing. We don't want it. Sometimes it's unavoidable. That's the way it is. But a positive y-intercept is something that we don't want to see. We want to see our data go through the origin. That means that there isn't any kind of FCD or skin that we're being poked by, essentially. But if you have data with a positive y-intercept, you just move that analysis line up and match the slope of the data the best that you can. You should not have a negative y-intercept. If you have a negative y-intercept, what that means is if you think about it, the data kind of starts straight and then curves upwards, right? Sometimes that curvature upwards is very slow and it's harder to catch. Typically what people do is they'll match the line to that curved data and it gives them a negative y-intercept. That means that you've most likely analyzed transitional flow data instead of linear flow data. The proper use of this plot, the best you can do is the data going through the origin. If you do have a skin or productivity loss, you have a positive y-intercept. You do not expect to have a negative y-intercept. So we're talking about that solid black line, the slope of it. There's another line on there. It's a dotted line. It's vertical. That's our time to end of linear flow line. And what you want to do with that one, and remember, we talked about earlier this morning, the two things we can get from data is productivity and volume. Well, the slope of the black line is our productivity, and the vertical dotted line is the volume, and we call that our T-alph line, right? So that's the time to end of linear flow. And as the user, you want to place that line where you think the linear portion has ended and the upwards curvature has begun. And so in my three examples here, you can see I would have a small volume here, but if this was the blue reservoir, that would be a bigger volume, and then the red one's bigger still. So the further you move that line out, you'll notice the OIP value that you have on the left-hand side of your screen will grow bigger and bigger and bigger. So let's take a look at it here. I'm going to expand this out. I'm going to stretch this up. I'm just going to hover my cursor over the top so I can stretch it out a bit. And you can see kind of a straight line signature and an upwards curvature. Now I can place this line wherever I would like through the origin, what have you, but we have a great button on top that links it to the origin. I love this button. I'm going to click it right here. And then from here, I'm just going to place my line through the data where I believe that straight line portion is. That gives me my LFP number. Notice how if I made it flatter, that LFP number is going to increase, and substantially so. So I'm going to put this through here, something like that. Now this is my time to end of linear flow. And for this one, what I'm going to do is I know this is data that's bounded. And so it's kind of coming down like this, down like this, down like this. And so I feel like around in here is where my volume would be. So I'm going to move it something kind of like that. And so I have my productivity here and my volume like that. And for many years, this is the way that we would analyze our wells. And we would go from this to a single phase model, and then from a single phase model to a multi-phase model. But now we have multi-phase methods, and we're going to talk about two. We're going to go through the flowing material balance, and then we're going to talk about numerical RTA. And numerical RTA is kind of where everything kind of comes together. And numerical RTA is the most challenging part of our interpretation, but I'm going to give you some tips and tricks to kind of find your way through that module. Okay, let's click on flowing material balance. So far, now I'm not really looking at these numbers, but you could say we did get some numbers. But in my mind, everything we've done has been qualitative. Okay, we've set the stage of what we're thinking. We know more about our data quality. We know more about our flow regimes. And now we're ready to get quantitative results to better understand the system that we're looking at. And so the next thing we want to do is to go to the flowing material balance. Now, if you click on the flowing material balance module, click on Run. I'm going to show you a quick slide here. Okay. If we had a perfect data set, okay, perfect. What you would find is the data would be the blue line that you see on your screen. It would curve upwards, and then it's going to come over. What I'm saying to you is that analysis line, that black line that you see on your plot, however you place it, the more vertical, the lower the volume, the flatter, the larger the volume. And what we want to do is we want to place this line as flat as reasonably possible to capture the volume that we think this well has seen. Now, the data on your screen is going to look a little bit different, and I'll explain that in a moment. But theoretically, this is the way it should look. So this would be the early time data. Notice how that slope is going upwards, right? So that'd be a lower volume. I get a little bit more data, then I would get line number 2. So my volume's increasing, and my volume's increasing until I finally kind of get to near the end of my data, that late time data, and I kind of get a really good sense of what that total volume would be. Now, the challenge is if you have a well that's in linear flow, and so let's say you're at like 0.3 here, okay? So you're more likely going to get more. RTA cannot tell you what's going to happen necessarily in the future in terms of how far that pressure pulse is going to go in your reservoir. And so if you're well presented in linear flow and you use flowing material balance and you get the volume, what you would then do is use the base model to get that model match. And then you could run those different forecast sensitivities on different fracture half lengths in order to kind of see the range of possibilities of future EUR. It's challenging for people when they haven't reached bounded flow to try to infer what the total volume will be. But when we're doing a base model, we're not playing those games yet. We're just trying to develop a model based on what the data is telling us today. So if it's in linear flow, it's in linear flow. If it had a contacted volume of whatever, that's what we're going to stick with to get that initial match. Then after that, we can start to play the what if game, right? And typically I'd make another scenario for that. Okay, so that's the way we want to see the data kind of clear up like that and flatten, flatten, flatten. Now, what you see on your screen is something a little bit crazier. And what happens is, especially with oil wells, is that you'll get that curve. And we're going to zoom into the bottom left, so you're going to see that curve a little bit more clearly. But then when we go below the bubble point, there'll be the GOR just kind of makes everything a little bit crazy before it kind of tightens up at the end. But what's really great is that in that period one, that first period we're going to be focused on, we can get a really good estimate of the contacted volume depending on how long it produced before it went below bubble point, okay? And so what we're going to do, our strategy for oil wells that have kind of messy data, GOR all over the place, is we're going to focus on that early time data as our initial estimate. Now, how do we know if that's correct or not? That's a question that is a good one. With flowing material balance, it is very clear when you've chosen a volume that's too small for your system. It's very clear. It is not as clear when you've chosen a volume that's too big for your system, okay? So if you're going to make a mistake with the flowing material balance, or if there's going to be a misinterpretation, it will be that you've made the volume too large, way more likely than you've made it too small. And so we can take some comfort in understanding that we're going to try to use the flowing material balance to get a value, but we're also going to gut check that value, that volume, when we get to numerical RTA as well. Because what makes your case stronger in terms of getting a consistent match is that when you have different analysis types pointing you to the similar solution, you're trying to build a story, almost like a legal case of what the best analysis for this well is. And so we analyze with the flowing material balance without any fear. We do the best that we can because we know we can also kind of check that on the back end when we get to numerical RTA. So let's go back to the software here. This is all the crazy data. I'm not really interested in that at the moment. So I'm going to use my cursor here, and I'm going to left-click hold to zoom in to the bottom left portion of the data, okay? So here I go. I'm going to left-click hold. I'm going to just zoom in. I'm going to create a little box, kind of something like that. And notice how we can start to see that curve that we wanted to see, right? It's kind of coming up before things went crazy. And so what we want to do is to place this line as reasonably flat as we can through the data. Okay, now we have to, the end's kind of a little bit messy. I'm going to place it kind of something like this. The value I like from this when I really did a hardcore study of this well, and you can type in a volume if you want, is I'm going to type in 900,000 barrels. I'm going to type 900 in there. When I type that in, it's going to change the slope of my line ever so slightly. And then what I want to do is I want to place it through here. Because what my eye is telling me is that as this data is kind of coming up, that is the current projection of where it would go. If it was in linear flow, I would still do it the same way, knowing that later on it would get flatter in time. But here I placed it at 900,000 barrels. It's going through that data. And I want to double check whether I have enough volume. I said to you, it's easier to know if you've chosen a low volume versus a high volume. Let me show you what I mean by that. Once you've placed your line, now, if you're at 900,000 barrels, leave it where it is. Don't do what I'm about to do. I'm going to match the earlier portion of the data. I'm going to do something like this. If I move that line too early in the data and I click run, I want to draw your attention to the plot at the top right. What that's going to do is it's going to give me a simulation of average reservoir pressure and wellbore flowing pressure. So let me just expand this for a moment here. This really doesn't make sense, right? How can my bottom hole pressure be higher than my average reservoir pressure? So I know that this is too small a volume, right? It just doesn't make sense. If I made the volume even smaller, my average reservoir pressure would be way below my wellbore flowing pressure. That doesn't make sense. Now, once again, if I place this line kind of like this, I add a huge volume to it and I run it, that average reservoir pressure line is going to rise up. Now, the more volume I give it, the flatter it's going to be, and it's going to extend up. But how far up should that line go? That's harder to understand. And so what we need to do is to use the data, to leverage the data the best that we can to identify where it should exactly sit in. So I'm going to put 900,000 barrels in again. I'm going to click it here, and I'm going to click run. And I encourage you to click run as well. And let's see where that average reservoir pressure line kind of sits on our data. Okay, so it's pretty close. Should it be higher? Well, the data is kind of telling me 900,000 barrels is fine, but I know it's consistent in that I have my average reservoir pressure above my wellbore flowing pressure. Okay, so flowing material balance, the point of it is to get your contacted volume. It is just an amorphous blob value that we then give physical sense through lateral length, through height, through porosity to get resulting fracture half lengths. And so the first number we care about is this 900,000 barrels. Let's click on numerical RTA. This is the big one. This is kind of the main event before we go into the numerical model. And I can see we're just a couple of minutes from break time. So I'd suggest as we take the break now, because when we come back, we're going to go through numerical RTA and we're going to wrap up with our model. We'll do a forecast. And if there's time, we'll do some probabilistics on the back end as well, which is super exciting. I love doing probabilistics on my wells. But numerical RTA is the main event. So let's take another 10-minute break. Let's get some coffee and some water, and then let's be ready because numerical RTA is going to require our attention to get to that final match that we care so much about. So I'll see you all in just a few minutes.
The slides done rolled on by, and the clock is nodding slow. In the Whitson course room glow, rate transient analysis on the go. You've been watching every curve, every dip and every sign. Now it's coffee for the mind, time to lay that burden down. If you need a little help, don't keep it to yourself. You know where to send it off and let that worry drift on by. It's break time now, my friend. Take a little breath again. Break time now, my friend. We'll pick it up when breaks come in. If you've got a question, send it through support@whitson.com or type it in the Teams chat too. That's the place to lean on through. When you come back, we'll carry on with the next part of the road. Same old screen, same steady load. Learning what the numbers show. Ain't no rush and ain't no race. Just a little pause between. Let your thoughts unclench and rest. Then we'll meet back in the stream. If you need a little help, don't keep it to yourself. You know where to send it off and let that worry drift on by. It's break time now, my friend. Take a little breath again. Break time now, my friend. We'll pick it up when breaks come in. If you've got a question, send it through support@whitson.com or type it in the team's chat too. That's the place to lean on through. Set your cup down slow, stretch your boots out wide. You've done a good job so far, let that honest effort ride. It's break time now, my friend. Take a little breath again. Break time now, my friend. We'll pick it up when breaks come in. If you've got a question, send it through support@whitson.com or type it in the team's chat too. That's the place to lean on through.
Well, the screen went still and the coffee's gone cold. We've been learning all morning, now the nerves can unfold. Great transient analysis got us thinking all day, but the clock says pause, darling. We can breathe for a spell. Lay your notes right down, ease that furrowed brow. We'll take a little rest here and come back around. It's break time in the Whitson course. Set your hands down easy, let the minutes drift across. It's break time, don't you fret no more. We'll be back in a moment, then we'll ride that learning tour. If you've got a hard question, don't you keep it in. Send it off to support@whitson.com, let the help roll in. Or type it in the team's chat, let it ring through the wire. There's a hand on the wheel now, keeping things on fire. No need to rush it, no need to guess. We'll catch every answer and do the rest. It's break time in the Whitson course. Set your hands down easy, let the minutes drift across. It's break time, don't you fret no more. We'll be back in a moment, then we'll ride that learning tour. Take a breath, let it settle, watch that worry fade. We'll return with fresh eyes and a little more gray. Yeah, the day keeps moving, but the pause feels right. One good rest can make a hard thing a whole lot lighter tonight. It's break time in the Whitson course. Set your hands down easy, let the minutes drift across. It's break time, don't you fret no more. We'll be back in a moment, then we'll ride that learning tour.
Logging, leaning, you made it this far. Screens full of numbers and charts to spot. Take a quick breath, let your shoulders drop. We've been running the flags, now the clock says stop. So grab your tea or just stretch out. The next few minutes are yours, no doubt. Got one question, don't let it hide. It's break time in Whitson. Today's break time. Let the noise fade away. It's break time. Virtual course, alright. Come back refreshed and we'll take on the night. If you need a hand or you got stuck, send support. And no, don't wait, don't lock. Support at Whitson.com. That line still shines. Or drop your question in the team's chat line. Keep it moving, keep it clear. We'll meet right back when the break is near. Got one question, don't let it hide. It's break time in Whitson. Today's break time. Let the noise fade away. It's break time. Virtual course, alright. Come back refreshed.
Okay. I got some questions coming in, so I'll attend to those before we jump back into the software. I've got 3, I think. Saul, I'm wondering whether the workflow changes depending on whether it's an up dip or down dip, or if that information is used more for interpretation. So really, what does it mean when I look at the well and it's up dip versus down dip? And that's a fantastic question. Really, it doesn't change the steps that I'm going to do. It's not going to change how I approach the analysis. But what it means to me is that if this well is acting differently than other wells that weren't up dip or down dip, then I want to see kind of what those changes are. And it can get very complex. There's an up dip well that I analyzed a couple of years ago where what happened is it went into more of a gas phase as we went up, and we weren't expecting that. And so that well looked like a gas well compared to the wells around it. So what I'm doing is I'm using the up dip or down dip to try to just get a sense of if it's different than the other laterals that were more flat, and maybe kind of why that was happening. And so the steps would be the same, but that's one of the things I would lean into to explain why there might be an inconsistency. Or if there's some weird kind of slugging happening because maybe I have an up dip well and I get more liquids flowing down or something like that. So I'm trying to find an explanation for why I might see a characteristic in the data that, in my personal opinion, wouldn't be common. Okay, so I hope that answered your question, Saul. Michael has one. Why did we choose 900,000 barrels in the flowing material balance section? Well, there's a couple of answers to that. The first one is I feel like that is the most honest line that I can place with the largest volume. Now, you'll notice that you can tweak that line a little bit. And if you tweak that line a little bit, you can end up with something I think as low as about 500,000 barrels, and maybe you could get it up to around 1,400, 1,500 barrels. And so what we want to do is to get the best estimate kind of in the middle, and then we want to see, and we're about to do it right now with numerical RTA, whether it's consistent with what numerical RTA is trying to show us. So we'll go through some more of that workflow, and hopefully that'll make a little bit more sense there. Duck asked, how much OIP do I get for my type curve? Because he got about 650. Here's the thing. On the type curve, we don't care about those numbers. We don't, once again, those numbers were generated for a different system. Theoretically, you could get the same volume. That's true, but that's not the method I would use to get my contacted volume. And so when we're in the type curve specifically, what we care about is the shapes. And so that's what we really want to lean into when we're in that analytical RTA component. Aiden had a question. How useful is analytical RTA when looking at multi-phase reservoirs such as retrograde condensate? Would it just be used as a baseline or comparable overestimation? Okay. So here it's a great question because it really talks to how deep do you want to go with the data you have, okay? So let's say it's Monday morning, I have a meeting later in the morning and I'm being asked to kind of figure out how different wells are acting with each other. I could go through and do a full RTA analysis on a lot of them, depending on the time, but analytical RTA will give you a pretty good set of how those wells compare to each other. So if there is pseudo-time issues and they're comparable wells, my thinking would be is that would affect the volume more than the productivity, and the productivity is really what we care about in early time. And so if there's an error in there, it would be more systematic, right? And so they would kind of, as comparisons to each other, would cancel each other out. So it is still useful for that, but we need to understand that we're kind of taking that kind of middle view of what it's capable of. We would want to go numerical if we really wanted to get down and dirty with the actual results. There's a couple comments afterwards about like condensate banking. Is that right? Let me see here. Yeah, liquids dropping out. Would that act like a boundary? Well, I mean, I guess it really depends. If you have a lot of condensate banking, that could be something that shows up as a productivity loss. And what we'd expect to see is there would be a productivity loss through time. And I'd expect to see a productivity loss through time before I see a volume change, right? And so if that banking is really cutting us off from volume, we only really know that if we've hit our boundaries and then it's been removed from us. You know what I mean? Because like if I'm in linear flow and that condensate banking's cut off some of my fractures, I wouldn't necessarily know that because I'm free flowing until I hit my boundaries. And so what I would then be looking to is whether the productivity of my well is decreasing as that condensate is falling out. And if that's the case, then I would be suspect that maybe I have lost some volume as well. But it's really hard to quantify that unless it happens later in the well's life when we really get that strong signal as to the contacted volume before it's removed. We don't know if volume's been removed from us before we've seen it. Right? When my kids spend money before I see the money, I don't know how much I've lost, but I can tell you when the money's in my wallet and it goes missing, I can tell the difference. And so that's really kind of one of the struggles that we have. And this isn't just an RTA thing. This is just with production data analysis. We can only know what we know based on what we've seen. And for the well, keep in mind when it comes online, it's in a mode of discovery. Right, in that early time, then it hits its boundaries, and then once it's bounded, it's really kind of mature. And when it's mature and it kind of knows the rules of the game, if something gets taken away after that, it's very clear to see it. In Haynesville wells, for example, it's a pretty clear signature where it's so overpressured. That doesn't happen with all Haynesville wells, but some of the ones I've analyzed where the fractures just kind of close in on themselves. And so you have a contacted volume that was very clear before, and then everything just kind of crushed in on itself. And then the new SRV, the new stimulated reservoir volume, is a lot lower. And so condensate banking, I would chalk that up to a productivity loss until I could kind of get other information that I'm losing volume. And for up dip, down dip wells, really for me, that just helps explain maybe what I'm seeing with my gas oil and why it might be different from other flatter laterals that I've seen. And then when it comes to the type curve, we don't really care about the numbers there. It's really a qualitative analysis. So I really appreciate your questions. Okay, let's share the screen here. Okay, so we're in the last part here. And so we're in the home stretch. And the home stretch, we need to go through numerical RTA and the numerical model. Now, numerical RTA, if you've never seen it before, when you load it up for the first time, it can look a little bit overwhelming. But I'm going to walk you through the steps of what you're seeing, and very quickly, it's going to start to click, and I'm going to give you some methods to use with it, and it's all going to come together and into focus. So let's look at that together. So if you're on the screen, just click on numerical RTA here, and let's click Run. And as that runs for you, I'm going to bring up my slide deck here. Okay. paper on numerical RTA really talks about this all very well. And so what I'm giving you is kind of a very short version of it. But the reason you'd want to use numerical RTA is that it handles those multi-phase systems. And so if you have that gas condensate system, if you have an oil well, we're going to be able to capture those GOR profiles, those WOR profiles, which can affect what we were looking at from an analytical point of view. And so as the systems that we go after, as the assets that we go after become more and more complex, numerical RTA is a great tool. You can almost think of it as a multi-phase version of the screwed time plot. It's not, but there's similarities there. And so that's a great way to think about it. Now, this is based on the Bowie workflow that came from a paper that was published in 2020 between Braden Bowie and myself. And what was really interesting was that when we looked at a number of different wells, some things became clear and some things we kind of knew before, but Braden found something that I had never considered before. And I still think it's absolutely brilliant. If you have, let's say we have two wells, right? They're exactly the same fluid, same completion, same everything, same drawdown. If those two wells have the same productivity or the same LFP, their linear flow will look exactly the same. And that kind of makes sense, right? Like if they're the same, we're drawing them down the same, they're going to have the same characteristic in linear flow. This is the one that I had no idea. If you have wells that have the same LFP and volume ratio, they're going to have the same behavior for GOR and water cut. And that's really kind of the linchpin that makes numerical RTA work so well. Now, finally, the last one kind of makes sense as well. If we have the same productivity and same volume and they're the identical wells and the same fluid and they're being drawn down the same, their whole history will be exactly the same. Now, why is that important? Well, that's important because the way numerical RTA works is where you're going to run a numerical model on the background and we're going to tune that model to the actual data. So when I talked to you about the workflow earlier this morning, I talked about 4 buckets, right? Data diagnostics, interpretation, modeling, and forecasting. Numerical RTA kind of breaks the rules a little bit because it takes the modeling and the interpretation, it kind of molds it together a little bit. And so on your screen, what you're going to see is this general layout. The top left is the Bowie plot. That's the one we're going to interact with. Okay, so that's the one we're going to interact with to understand what's going on with our data. The other plots are there for our information to help us find the right rel perm changes or our PVT changes that might be required to get a match. So at the top right, you'll see your GOR. You can view it in terms of cum or in terms of rate. That's true for all of the plots that we see here. We have cumulative volume right below the Bowie plot, and that's the one I'm really going to focus on as well. We have cumulative gas, and then we have water cut at the bottom left, and then the pressures at the bottom right. Now, the pressures will generally match, okay? And the reason for that is the numerical model that we're running on the back end, we're taking the PVT information, the bottom hole pressure information, the rel perm information, and it's generating a model based on that. And so on the top left, that Bowie plot, we have a horizontal line, and then you see these other lines coming down. These are for volume. The placement of the horizontal line is for linear flow. That's your LFP. The higher you place that line, the higher the LFP, the lower the LFP. So let's talk about that a little bit more. If we think about the model, the numerical model being run in the background, when you move this vertical line on that top left plot, that Bowie plot, you move it up. What you're essentially doing is taking the model that was been run and you're giving it more and more fracture half length. Okay, so you're increasing it until it matches the general straight trend of the data that you have. And so where the screwed time plot had linear flow as a straight line at some slope and then an upwards curvature for bounded flow, what I'm saying to you is numerical RTA, linear flow presents itself with a relatively horizontal line and bounded flow has a downwards curvature. And so as you move that horizontal line up to meet your data, what you're actually doing is resizing that numerical model to match what that early time data, that linear flow data actually did in your well. And then we care about volume. So this is the productivity portion. And volume, we're going to try to get one of those bounded lines to kind of curve with the data with us, right? And so this would be a larger volume, the purple one, and blue would be that smallest volume. The sooner that line deviates and goes downwards, the smaller the volume, right? The more we can push that out to the future, the larger the volume. Okay, so let's do that together. Now, I'm going to zoom out a little bit. The way that I use this plot, there's specific steps. First, we want to place our line on the Bowie plot. Once we've done that, we want to take a view of the water and the gas. Typically, the water and the gas won't match right away. Our strategy is to fix water first, then fix gas. That is our strategy. So what I'm going to do is I'm going to raise this line up. Now I'm going to stop raising this line up when this yellow line, and the yellow line is just the model that the software is currently selected, okay? What I want is I want this yellow line to match my green line as close as possible. So I'm going to move this line up. Yeah, that's pretty good, but can I get a little bit better? No. Okay, I'll move it up a little bit more. I'm going to move that line up. So I'm looking for is because oil is what I'm using to understand my system. I could choose gas or liquids, water perhaps, but oil is really what I'm using to understand my system. I'm really focused on the Bowie plot, the placement of this line, but I'm using this Cume plot as my guide. Okay, so I've placed the line there. I have the yellow line going through, and now I want to kind of survey what's going on. If I look at my GOR, I can see that my model GOR is a little bit low. That's clear to me here because my gas is a little bit low here as well. I'm going to come down here and look at my water and look at my pressure. Now, my pressure is probably going to be just fine, right? Because that's what's being fed into the model in order for me to create the model in the background. But my water is a little bit low. And there's a couple of different strategies we have to fix that. If we don't know what the water saturation is, we could change water saturation. But if the water saturation is kind of locked into place, if that's something where that's a value that is trusted, then what we can do is modify our rel perms in order to get that match. Now, there's different ways that we can play around with relative permeabilities. This cheat sheet is in the slide deck that you have, and this is a guide that I use. It's another printout that I have at my desk, which allows me to kind of tweak them in order to kind of get what I'm looking for. But typically, in numerical RTA, the only things I'm really trying to change is SWC, which we'll do, and maybe NG. And I'm not sure if we're going to need to change NG this morning. Okay, so this is the cheat sheet. You have it as one of the slides. If you print it out, it's a great thing to have at your desk. So I'm looking at my water match. All the models are matching low. So at the bottom left, you should see something that says relative permeability. If you don't, that means you're zoomed in too much in the web browser. You need to zoom out a little bit. If you zoom out a little bit, you're going to see rel perm tucked away at the bottom left here. So rel perm is here. I'm going to click on this box opener here. And when I open it, I am faced with relative permeability information, which is fantastic. Now, there's matrix rel perm and there's fracture rel perm. We're going to stick with the matrix for now. Fracture really modifies how those early time fluids act. I'm not as interested in that. I want to know how the reservoir overall is acting. Now, the great thing is if you have a type curve area, what you can do is kind of find what the rel perm curves are for a few wells, and then you can save that as a template. So when you analyze another well, you can just pick it down from the template, it pre-populates it for you, and you can move forward. But let's talk about that for a moment more. If you analyze a well and you get a custom set of rel perm curves, is that meaningful? I would argue it's not for a single well. If you analyze multiple wells within a type curve area and they were all converging to very similar rel perm values, then I think that's something that's valuable, because the wells should act similarly. If they didn't, they shouldn't probably be in the same type curve area. And so the goal that you would have for the area that you're looking at is to have a type curve area with a single set of rel perm. Maybe there's minor tweaks that's required for the odd well, but generally speaking, that would be the goal. And so you'd want to start with the well that has the best data in your type curve area. You want to lean into those wells that have high quality data. And you would use that to try to get a sense of what your rel perms are. And then you would cascade those rel perms to other wells to see if you get similar matches, if everything's clicking into place. Because what you're really trying to do is find out, okay, what rel perm should I use if I'm going to create a model to see what a new infill well would do, or a new pad of wells. And so that's a really great way to go about it. For this one here, I'm just going to take my SWC, it's at the top left there. I'm going to drop that down to 8. Now, why am I choosing 8? Well, because I've analyzed the well before, okay? Usually with rel perm, what you do is you just kind of try a low number. Sometimes it's too low, and then you bring it up a little bit, then you bring it down a little bit, and then you kind of find where it kind of fits. And so for this well, I know it's 8%, but usually I'd start with 10, and I would see that the water match would be too high, and then I might drop it to 5, which would be too low. And that's how we use rel perms. You kind of overshoot it a little bit, and then you converge on the value that's going to give you the response that you're looking for. So I'm going to go ahead and click save here. And anytime I change anything, when I change my rel perms, I need to click run once again. Now, when I click run, I'm going to have to change that line on the buoy plot again. So I'm going to do that again. I'm going to bring it up like this. So now my oil's matched. My GOR improved a little bit there, which is great. And you can see that my water's matching just fine. Now, the volume we got from flowing material balance was 900,000 barrels. So what I want you to know is we can take that in and test it out and see if it makes sense to us. And the way that we do that is we can lock various things in numerical RTA. I really like locking my volume. I think it's very helpful. So here you can see that the initial model match was saying about 1,400,000 barrels. I want to try 900. So what we're going to do, we're going to type 900 in there. But after I type 900, I want to lock it into place. Now I've locked it. See how it picked a volume that was lower? It's further down, right? Because the further down it goes, the lower the volume. And so now what I need to do is to rematch my buoy plot once again. I'm going to grab that horizontal line. I'm going to drag it up. I'm going to try to match that oil. And you can see my gas is a lot closer. So that volume, remember, volume really dictates that GOR profile. And so now with the flowing material balance, I'm trusting that value I got a lot more because it's giving me that oil and gas value that I trust. And so I typed 900 in here, I locked it, and then I moved the LFP line up until I got that oil match. Then I looked at gas and GOR, and everything starts to come together. Okay, so that's the strategy. Use the buoy plot, tune it, look at your cum oil. If it was a gas well, you'd look at your cum gas, right? And you would have gas and water. You'd modify the water, get the best gas match you can, and then we would go to the model. For oil, we want to tune it, the LFP, just to get that cum oil looking good. Then we want to tune our water, run it again, and then if we need to make rel perm changes for gas, we could do it. But if the gas is behaving, which it appears it is here, we can just then move to the numerical model. So those 4 buckets that we talked about this morning, we had data diagnostics, interpretation, modeling, and forecasting. Numerical RTA is the final step in interpretation. From here, what we want to do is we want to move to the numerical model. Now, the way that we do that is we're going to take all these parameters. You notice that it gives me a sense of my parameters. It gives me a sense of my permeability, which is around 12 nanodarcies in this case. It gives me a fracture half-length estimate, which is about 360 feet here. And so what I want to do is I want to take that into the model, and we have a very easy way to do that. What I do is I click on the Send To button here. When I click on that, I'm going to get a pop-up. Now, this pop-up is going to ask me what well control I want. Okay, we're going to leave it as gas, but I'm going to touch on that in a second. The other thing is it wants to know whether I want to include the data filtering that I did through my interpretation or not. And I do. I want to include my data filtering. So I'm going to click on that, and I want to click Export. So let me do that once again. I was a numerical RTA. I clicked on Send To, Gas, Include Data Filtering, and then I clicked Export. And when you do that, it's going to open the numerical model for you. Let's talk about the numerical model. Numerical model is going to allow us to match all of the fluids and the pressure. You can see we have the oil, the gas, the water, our bottom hole pressures, the GOR profile, and our water cut as well. We have 3 tile cards at the top. The one to the top left is usually the one that we would modify. So you can see the lateral length is here, the height's carried over, compressibility's there, number of fractures, a lot of the things we saw in the scenarios tab. But the value we've added is we have a fracture half-length that we brought in, the permeability we brought in, and we did talk about these gammas, right? We kind of opened with that a little while ago. For gamma, to give a better explanation of that, we have a plot up here, and it's pressure-dependent permeability. I'm going to click on that. What this plot is showing you is how the effective permeability changes, we could say through time, but really it's through depletion. So here you have your effective permeability, and here you have your pressure. And what I'm saying to you is that when we first start producing this well, our effective permeability is 100% of that 12 nanodarcies that we have. But as we produce and we get down to, let's say, about 3,500 or so PSI, the effective permeability is only at about 50% of what it was before, around 6 nanodarcies. If you have an overpressured reservoir, I don't typically start with a gamma value. I typically leave it at 0. Okay, now the reason I do that, and you don't have to follow me, just give me a second here. The reason I do that is if I don't know what my gamma is, when I analyze the well, the one thing that I know typically is that gamma won't affect my early time or early production. It'll be more later in time. So if you have an overpressured reservoir, and by that I mean anything about 0.65 psi per foot or higher, that's when I start to think maybe we might need some gamma. Above 0.7, I'm seriously considering it. I don't add a value. I analyze the well like we have already. And then what I do is I look at the numerical model. What I'm hoping to see is an early time pressure match, right? So I expect the simulation to match the early time pressures, but in later time, I expect there to be a difference between my simulated pressure and my real pressures. I expect my simulated pressures to be higher. So another way to say what I've said to you is that when you add gamma, it takes your late time simulated pressures and brings them down. Okay, and I'll make a little bit more sense after we run this model. Let me close out of this. So we have our permeability, our gammas. This would be that skin that we were looking for in analytical RTA, that FCD. It's at 1,000. That's considered to be infinite, so we don't think that we have a skin on our system. Now we can have multiple layers. We have a lot of different options here for an region model, asymmetric lengths, all sorts of stuff, right? But when I'm doing a base model, I want to keep it as simple as possible and then only add complexity as I need it. Let's go to the next tile card here. This one, I normally don't change a lot here when I've already gotten to the model. I have my water saturation, my GOR, my initial pressure. I usually don't want to change my initial pressure because that is so fundamental to everything that I've understood through my interpretation, but it is there. And finally, we have that relative permeability. And this is going to look very familiar. It's exactly the same thing that we had from numerical RTA, and it just kind of carried forward for us here. Now, at the top, we have different types of time stepping. Smart means you're going to get a lot of points in early time and then periodic points later. It allows the model to run faster. That's the advantage. You can do custom, so you could say, I just want every other data point. Or you can do all, where you just want all the data points, okay? Now, custom and smart are really helpful when you have wells with a really long history, or if you have data that's at a higher fidelity than 1 point per day, right? If you're getting every 6 hours and you have 2 years worth of data, custom and smart will definitely get you that model match a bit faster, but you can usually use between smart and all. I like to use all. It runs a little bit slower, so let's stick with smart just for now, and we'll move to all in just a moment. Now, on top of the data points that you want to use, there's different types of gridding that you can use. The default is low. You can go to very low, and you can go to very high. Keep in mind that the law of diminishing returns is in play here. If you add more grids, you will get a slightly different answer at the cost of a lot more time waiting for the model to resolve itself. So if I was doing like the final run on something that was like super important, I might put it at medium or high. Very typically, I leave everything at low, but I leave that up to you. It's something that when you've analyzed a couple of wells, you can run it in both ways, see if there is any meaningful difference between the two. Typically, I don't see anything that would change any type of business decision whatsoever. And so I find low is really a great way to go. But if you want to try it, very high is available for you as well. Let's talk about well control. Well control is the perspective that you have on the well system itself, okay? Now there's different options here. You can use oil, gas, water, liquid. You can use the synthetic bottom hole pressure, which is really cool, or the real bottom hole pressure. What I'd recommend to you is for oil wells, I find gas does the best job for well control. Gas is very compressible. It's like a kid that's just wants to tell you all about its day. It has so much reservoir signal in it. I find that it's a great way to understand that oil system. If I had a gas well, I usually start using gas for a gas well also. But what you'll find is if you're in really high drawdown, if you're at 80, 85% drawdown, a small change in rate can have a huge swing in the simulated pressures. So if I'm in really high drawdown, I use my gas, I use gas as well control, try to get the best pressure match I can, even with all the noise, because when I use bottom hole pressure as my well control, everything's going to look really great. Okay, so you want to strive to get the best match you can from the gas perspective, then flip it to bottom hole pressure when you have those high drawdown gas wells. So another way of looking at well control is it's very much like if you have a family at a Thanksgiving supper and politics comes up, a little dicey, and you have to have an opinion, right? You have to make the choice of which phase or pressure you're going to view the perspective of the well through. And I have found consistently for oil wells that gas is a great conduit to understand what that system is doing. Now, if you have gauge pressures, if you have super high quality pressures, you probably want to use those, right? Because you really have higher confidence in those values. But if it's calculated sand phase pressures, I feel like there's a bit of noise there. Gas is really the way I like to understand my system. Once again, if it's a gas well, depending on the level of drawdown, you'll notice that one match will look better than the other when you look at it from the bottom hole pressure perspective versus the gas perspective. So we have to make a call if we're going to use the model, and I'm going to suggest that we use gas. So if you have smart, low, and gas, let's run the model. Okay, the black line you see is the simulation. Okay, so it's going through, and what we fed the model was the gas through time, and it generated the oil match for us, the water match for us, the GOR, and also the pressure history match. Now, our match is pretty good. If it wasn't very good, let me tell you the strategy that I would use to fix it. Typically, I like to look at my pressure plot, but what I'm saying to you is going to be the same for oil, gas, and water if we care about water. And I'm going to touch on water in a second. Let me make a little note about water. The way to think about matching your model is you want to think in terms of those basic things that we have from the data, which is productivity and volume, okay? Productivity gives you a sense of the level of drawdown you're going to have. And the way that's visually shown to us here is that is the distance between this is simulated reservoir pressure, and this is our simulated bottom hole pressure. Productivity dictates the space between those two. So if I lowered my permeability, this black line would come downwards because it would need more drawdown in order to produce the fluids that we have. If I increased my permeability, if I put it a bit higher, tripled, quadrupled it, this black line would go closer to that average reservoir pressure line because the system is saying, I don't need to pull down as hard in order to produce the fluids that I have. Okay, so that's productivity. That'd be the same thing for FCD as well. FCD has a slightly different effect. It does pull it down, but it also makes everything a little bit more jagged as it pulls that black simulated pressure line downwards. The next one is volume. If I had height or I had fracture half length, what you're going to notice is that's going to change this line, your average reservoir pressure line. And the way that I like to think about it is if you had an infinite reservoir, like if you put your fracture half lengths at like, I don't even know, 6,000 feet or something crazy like that, that average reservoir pressure line would come up and it would be flat at the top of the screen. And so what I'm saying to you is as you use volume, what you're going to do is it's going to drag this average reservoir pressure line up, and it's going to bring the simulated pressures up as well. And so it's going to kind of angle everything a little bit more. So productivity is the space between the two, and then volume is going to kind of change the angle of attack. Okay. Now there's minutia there where things will happen a little bit, not differently, but things will affect things one way or the other. But generally speaking, that is the thought process I go through when I'm trying to figure out what I want to tweak in the model. Now, if my model match wasn't my favorite, there's different ways that I could modify the parameters in order to get a match that I'm happy with. One is auto fitting. Okay. Now, auto fitting is a great tool, but once again, just like data filtering, we want to be a little bit on point with it. Now, we've all done this. And so if you're all in your offices and no one's looking, when we're done today, I encourage you, click every box and click AutoFit because we've all done it. When I started at Phuket years ago, we would go through a training program, and once they took you through that training program, you were given a well, and you had to analyze it. You were given the well on Friday, and you had to present it on Monday morning. And it was a big thing, right? It was a way to prove yourself that you'd learned a lot. And so I was given my well. It was a gas well. And so on Friday afternoon, I went back to my really terrible apartment, actually, in Calgary. And I was ready. I was ready to spend the whole weekend analyzing this well because I was going to do a great job, and I was really looking forward to Monday morning. And so I got home, ordered pizza. I brought out my whiteboard. I was ready to go at it like in the college days. And I loaded up the software, did the interpretation, went to the model. My model match wasn't that great. And so I opened up the software and I clicked every single thing that was in the software. I clicked every single thing and I clicked AutoFit. And let me tell you, I got the most amazing match you could ever believe. I was so proud of myself. And I remember thinking to myself, it's embarrassing to admit, but I remember thinking to myself after pressing AutoFit on every single thing, that I'm really good at RTA. Like I finally found the one thing that I'm really, really good at. My analysis was impeccable. The model match was impeccable. And so I was done. I thought I was going to spend all weekend on it. I only spent maybe half an hour on it. And so Monday morning, you never saw somebody as confident as me. When I went in there Monday morning, I couldn't wait to share my results. And of course, as I went to the front of the room to tell everybody about the model I had done, I learned one of those lessons that you have to learn the hard way, which was just because your model matches doesn't make it a consistent model. And what I mean by that is the model match that the software had given me, I had permeabilities, I don't remember, but it was like 0.01 nanodarcies. I had fracture half lengths, which were like 4,000 feet. Like it was completely unreasonable, but the model looked awesome. And so what we want is a model that is consistent with the physical reality. What I mean by that is we want a model that is anchored into what the height is that we think it is, the porosity that we think it is, but also the well spacing. If I had had my brain in my head those many years ago, I would have looked at this and said, okay, what is the well spacing around this well? Well, the maximum fracture half length could have only been around 600 feet or so. And so I would have known that while my model matched, it was not a representation of what was physically going on. And if I was trying to match data where something changed, I should try to match the data before a frac hit occurred or something else occurred. Sometimes getting a model match through the whole history of the well, like we've talked about earlier, is not the proper model match. We want to know when it was consistent. We want to know when it was unperturbed. A lot of times you'll have a before and an after. So I don't do that anymore, but I encourage you to try it once. It's a lot of fun. So my rules for auto fitting is I will typically just do it on permeability. Most of the time, that's what I do. If I do have a well that has a skin, what I will do is I'll run it on permeability and fracture conductivity. Sometimes I will run it on permeability and NG. And I typically do that if I'm struggling to get a gas match or an oil match, from the gas perspective, that kind of lines up with my data. Now you can use auto fitting, but the other thing you can do is you could open up this tile card here and manually change the value. So you can type in values and then run the model and keep modifying it over and over. Now this model match looks pretty good. It's going all the way through. And so what we can also do is include a forecast here. Now forecasting in Whitson is so easy. And one of the things I really love about the software, so I just click this box here. I'm going to open up Edit Forecast Schedule. Is we can forecast the well in many different ways. We can do it based on constant pressure. We can add different segments, but we have this parametric decline, which is just really great. And what we want to do is to have that parametric decline kind of mimic what we think the pressure is going to do in the future. And so we can run this off of BHP or wellhead pressure. We can do a parametric decline, which is the kind of the curved forecast for that bottom hole pressure, constant, or we can do a custom schedule, which is great. We can forecast off of the last simulated bottom hole pressure or the last historical one, or we can specify a value ourselves. And we can also change the forecast start date. Now you care about that because let's say you had a well that was doing its thing for 2 years and then it was frac hit and completely changed afterwards. You'd want to move that forecast start date to the end of that last first part of the well's life so you could forecast it, then compare that to what the well's actually doing now to see how much you might have lost or in some cases gained because of whatever occurred. Down here, we can change the forecast function. I like to leave it as hyperbolic. We can change our segment end time. I'm going to leave it at 3650. And here's just the pressure information. But once again, if I wanted to add multiple segments to this, I could go ahead and do that. But I'm just going to leave it as a single segment for now. So let's click save here and let's run this. We can see the forecast come through. Now, let's say that we made a mistake on our volume. I don't think we did, but let's say we did. Let's say this was a well that was in transitional flow. Or let's say, well, we could do it with height or fracture half-length. Let's do the fracture half-length one first. What I'm going to show you is what we could do with our probabilistics. Once you have a model match, you don't even need a forecast, but it's helpful with the forecast. This is where you can quantify your uncertainty. So once you have a model, if you want a forecast, it's good. I'm going to click on probabilistics at the very top here. Now I'm going to click on include forecast. What this is going to do for me, this module, is it's going to allow me to put in distributions for different parameters. It will also allow me to re-auto fit the well, which is awesome. And I can do this up to 1,000 times. And it will give me a distribution of EURs based on the uncertainty that I have. And I can also export the values out to Excel and see plots of permeability versus fracture half-length. Another really helpful one is height versus fracture half-length, because typically the height, there's some unknowingness there. And so I want to quantify that if my height is off by, let's say, 20%, does that change my fracture half-lengths enough to modify the wells per section that I might be thinking about? So I'm in probabilistics. I clicked on include forecast. Let's click on the tile card right here. So once again, it looks like the auto fit pop up, right? Because we have all those different parameters that we can use. For this one, let's use permeability and let's use fracture half-length. I'm gonna click next. This is where I put my distributions in. Now, very commonly, what I don't like to do is to stack my parameters, right? I don't want to stack my height, fracture half-length, permeability, initial pressure, all of these things. Doing probabilistics on initial pressure is kind of crazy, actually. So I kind of want to just kind of see how everything's kind of moving together. And so very commonly, I'll use 2, maybe 3 parameters when I run probabilistics. For fracture half-length, this is the one that I really want to know, okay, maybe I misjudged it. Maybe it's a bit larger than what I currently have. And so there's different distributions here that I can input. I'm going to stick with uniform, but we have triangular, normal, log normal, and then we have that auto fit, which we'll touch on in a second. So for uniform, I can see here, my fracture half-length is currently 358 feet. So I'm going to put that in as my minimum value. But let's say I'm off and it's up to 700 feet, let's say. Let's go to 700 feet. Something like that. So now I'm telling the model, choose a fracture half-length from the one that we currently have up to something larger. Now, when you increase your fracture half-length, you do increase your volume. But if you remember that equation for LFP, it's 4 times XF times NF times H times the square root of permeability. And so what that means is as your fracture half-length increases, your permeability needs to come down to compensate. And so what I want to do is I don't know exactly what my permeability should be in every case. And so what I want to do is I'm going to click on auto fit. I'm going to click auto fit there. Now I'm going to put in some boundaries here. I'm going to put in some values. Now the max value I'd expect it to be is 12 nanodarcies because as my fracture half-length increases, that permeability should come down. And so the max value I'm going to put here is 12. And for a minimum value, I'm going to put 0. That's pretty low, but let's use 0. Once I have my permeability and I have my fracture half-length set up, then I can change the number of cases I want to run. Now I'm going to run this. I always like running it a lot, but let's run it for 20 runs due to our time constraints here. So I have 20 here. I set my matrix permeability to auto fit between 0 and 12. I took my fracture half-length uniform between 358 and 700. Feel free to modify that. Maybe you want to run a different case than I am. I'm going to click save. Now, once I've done that, everything is set up. All I need to do is run. So I'm going to run my cases. It's going to go through. Now, if you're running 1,000 cases, keep in mind it's going to take a while to run, but this is one of the great features of Whitson is its unlimited licensing. Now, what that means to you and me as reservoir engineers is that means you can have concurrency as you're analyzing data. Very commonly, when I'm analyzing wells for a client, I have about 4 or 5 windows open at a time because we can look at, especially if it's a pad of wells, when I tweak something here, I want to know what it does to that other well and back and forth. And so if you're interested in probabilistics, and it's a fantastic tool to have, what you can do is set it up, run it, and then go to the next well. Open as many windows as you want because of the unlimited licensing. So it's a really great feature that we have at Whitson. It's going to wrap up here pretty soon. It's going to give me a range of distributions. It's going to give me a P10, P50, P90. I'll be able to check the error, which is really important as well. And I'll be able to also look at the overall statistics once it pops up. Now, I can export this information as well. As you've seen, all the different images that we have in Whitson, it's very easy to get information into the product and out of the product. It's going to be a little bit slower because we're all running it in the same domain at the same time, so I expect that. But let me just touch on one thing while this is finishing up here. Back in my history match, once I've run it, there's this little check mark here. Okay, so I just went back to my history match. And if I hover over that, you're going to see something there that says history matching error. Okay, now mine was pretty good. It was under 4%, right? That's a gold start. That is a meaningful value, but it's not a hill to die on, right? We are not looking for everything to get to 0. That calculation is based on data points that have been selected or deselected. So the noisier your data, the more of those noisy data points you remove, the better your error will be. But really, we don't even really care about all the ups and downs and all the craziness in our data because the reservoir signal is not crazy. It's smooth. Anything we see where our data jumps up and down, that's operational. It could be a measurement error. It could be a lot of things. From the reservoir perspective, it moves more, I don't know, like an old elephant, I guess. And it just kind of walks nice and slow, okay? It's not going to jump around and move all around. So if you have the general trend of your data, it's not worth losing sleep over with your error percentage. Now, if you're going to do probabilistics and you've filtered your data, that does give you a better view of kind of maybe what range of error you'll accept from those probabilistic results. So here's my probabilistics results. They've pumped up. You can see the range that I have with those different fracture half-lengths. Now, if I had done a 50-year forecast, I probably would have seen that expand even more into the future. Now, what's great about this is I can click on the error at the top right, and I can set the level of error that I'm comfortable with. Maybe I want it down to 3%. If I choose 3%, or I can move this line down even more, I can then regenerate the plots, and it's only going to show me the cases that meet that error percentage threshold that I'm interested in. And at the very top, it's told me that half the cases that were run are good enough for 3% or better error. And so this is a fantastic way in order to quantify the uncertainty we have with values we've been given. This is also the method I would use if we had a well that was in linear flow and we do not know how far we're going to see. If this is a well that is bounded on either side, we can calculate what the maximum potential fracture half-length would be. We would set that uniform distribution to that and run it on permeability, and we should be able to get a match all the way through and see what those EUR, the EUR spread would be based on what we've contacted today versus what we might contact into the future. So we have different statistics here. I love the top 10. It'll give me a readout of all of my parameters. I can look at a quick summary of everything. And I can also look at the distributions. And so I can view it as a cumulative distribution function, P10, P50, P90. I can look at all of the different values that I have. It's fantastic. Or if you want to kind of get more into it, you can export it out to Excel using the case summary, and you can kind of plot the different parameters against each other. So for today, that was what we prepared for. And what we did was we looked at the overall layout of Whitson. We talked about fields, we talked about projects, we talked about wells and scenarios. We talked about how having a naming convention for our scenarios is really helpful because as we start to do more and more analyses, as our team would do a lot more, it can get pretty muddled. we went through and we looked at the production data, and we were looking for gaps in that production data because that can give us a little bit of an indication of something meaningfully changed with the well. And we care about that because that means we shouldn't expect a model to match through the entire history. We then went to the PVT and set that up with the equation of state. The bottom hole pressure, we calculated that right through with the wellbore configuration in the software. We then went to analytical RTA. We used the type curve. We used that for data quality checking to see if we had reservoir signal to filter out some of those data points, which we didn't trust very much. And then we got a general indication of our flow regime. But then for fractional RTA, we got a better indication of our flow regime. We used those delta values to get a sense of our linear flow, whether we had transitional or boundary dominated flow. Knowing that we were in bounded flow, we went to the flowing material balance. We got the first number we cared about, which was the contacted volume of about 900,000 barrels. We then went to numerical RTA, and we were primed up for that one. We know the Bowie plot's the one we're interacting with the top left. And we're going to tune that LFP line looking at our cum oil. We match our water first, whether we change SW, our water saturation, or the rel perms. And once our water is good, and I said I would talk about water. When it comes to water, we are not looking to match your flowback water. We want to match the water that we believe was in the reservoir to begin with. Everything is around material balance and points to an initial pressure. When we put water under the ground, we're increasing that pressure temporarily, but as we produce it back out, we've kind of messed up that material balance a little bit. So very clear, when we're using a reservoir model, the water we want to match is the reservoir water. Okay, so that's a side note. Once we're happy with the water match and numerical RTA, we tune our gas match if it's needed. Typically, that's with those rel perms. We're going to change NG, maybe NOG to do that. We then send it to the model. If our model match isn't great out of the gate, we can change different parameters. We can run auto fitting. We don't want to run it on everything. Usually just try it on permeability first, see how that works for you. Once we have a model match that we like, we can create a forecast very easily. And if that's all we wanted, that's fantastic. But then we can also do probabilistics on that. We can run probabilistics for different cases to quantify the uncertainty that we have. And that's what we've prepared today. So I'm going to see if there's any questions before we wrap up. If you don't have any questions and you wanted to jump off, I thank you very much for spending your morning with me. I really appreciate it. And if you have follow-up questions, please reach out to support. Please email support at support@whitson.com. And we look forward to hearing from you. So I'm going to check my, see if there's any last minute questions that came in here. Okay, so there's a question from Benham asking about oil and gas rates. Okay, so which one should you lean into? The thing with gas, the thing with gas, I usually find that if my gas is not being measured properly, that it also cascades to my oil, because typically what I see is that's an allocation issue. And so I haven't seen too many cases where my gas was garbage and my oil was good. But if that's the case that you have, then yes, you would want to lean into the oil a little bit more. And in that case, the problem is if your gas is really off, I would suspect that the calculated sand phase pressures are also going to be off as well. Pressure and gas are so tightly coordinated with each other because of compressibility that if oil is the one you trust the most, then sure, use oil in that case. But usually if I'm trying to get a pressure match and I want to get the oil kind of tuned in the best that I can, pressure is what it is. It's what I have to work with. Using gas is usually my best way to get that pressure and oil match together. So what I'd encourage you to do is analyze the well, view it from the different perspectives. If the oil perspective is giving you results that are closer to what's expected in terms of perm ranges and fracture half-length ranges, then yeah, I would go with that if that's the more correct one. Access to the recording, I believe so. I believe that this will be posted after the fact. Excellent. There'll be an email. Thank you. Thank you. Well, I appreciate everybody. If there are follow-up questions, please reach out to me or to support. And once again, we really thank you for being a part of the Whitson family. We appreciate it. And it's our pleasure to talk to you and to present various things to you. So thank you so much.